It's 2:40, so we'll go ahead and get started with the next session. Simulation. Good afternoon. My name is Siva, and I'm a researcher at Wabi. In this session, we will be discussing an important behind-the-scenes component of self-driving, simulation. A critical component to making self-driving vehicles a reality is verifying that they are safe. For example, how do we evaluate that an SDV will perceive an unknown or rare actor? Or how do we confirm that the SDV will respond accordingly to high-speed occluded actors? We want to test the autonomy system and ensure it can handle everything that may happen in the operational domain we want to deploy in. The self-driving industry uses a combination of 3 different approaches for evaluating SDVs: structured testing, real-world replay, and simulation. First, there's structured testing in a controlled test track. It allows us to test self-driving cars' performance under a set of reproducible safety-related events, like a vehicle driving past the SDV or pedestrians crossing the road. This test setting is considered high fidelity, since we evaluate the full autonomy system and vehicle hardware in the real world. We also consider this testing to be reactive. As the SDV perceives the scene and performs a maneuver, the other agents in the real world can respond to its behavior, and the sensor observations are accordingly updated. But the scenarios are limited. It's difficult to test extreme or dangerous situations, such as high-speed avoidance maneuvers. Additionally, large-scale testing is impractical. Another popular approach is to evaluate the SDV on pre-recorded real-world data. This is a common approach, as it's convenient for developers and researchers to run autonomy algorithms on offline datasets. This approach also provides a more realistic evaluation setting than structured testing, as more diverse urban and highway scenarios may be collected. But it's still hard to test a safety critical case, like pre-crash events, because we don't want to take risks to collect those events, and we can only evaluate on what we collect. Furthermore, pre-recorded logs are off policy and not interactive. This means the sensory data and other actors' behaviors are not updated according to the ego car's action, causing scenario drift. And the third method is to use simulation. While simulation systems have a domain gap with the real world, the agents and the environment in the simulation can be reactive. Simulation also allows testing any safety critical scenario easily and can scale to millions of scenarios for autonomy evaluation. And that's not all. In addition to evaluation, simulation provides many other additional benefits for improving the autonomy system. One can perform adversarial attacks in simulation that identify unknown issues in the autonomy system, generate unlimited annotated training data in a cost-effective manner, and even enable closed-loop training of the autonomy system to make it learn from its mistakes. We now reviewed the SDV autonomy system and the different ways one can apply simulation to evaluate it. The typical autonomy system ingests sensor data, perceives and predicts agent behaviors, plans a safe path, and then executes the controls that will generate that path. Some traditional simulators used in industry only simulate the actor's bounding boxes and trajectories, enabling only motion planner evaluation. This is easy to run and has relatively low overhead, as it only requires simulating the actor dynamics for traffic. But it makes the assumption that the self-driving stack is modular and does not evaluate perception errors that may compound and result in autonomy failure. Testing the full autonomy system requires going further than just simulating bounding boxes and trajectories. We need to have a complete simulation system that models the real world accurately, including the sensor data. We call this setting end-to-end closed-loop simulation. We simulate the sensor data of the scene, run the autonomy stack, and perform the SDV's output maneuver, update the actor's poses and behavior, and repeat for the full scenario. Closed-loop simulation has all the benefits mentioned previously. If the domain gap between the simulator and real world is small with respect to the autonomy system, and the closed-loop simulator is efficient, we can get a good signal on autonomy performance. The weakness is that this type of simulation has a higher computational burden than the previous simulator that only evaluates motion planning. And the minor downside of testing the full autonomy system is that it is harder to assign blame when autonomy does fail a scenario. In this session, we will be discussing what the necessary components are for an end-to-end closed-loop simulator, and the different types of approaches one can take for these components. To build a closed-loop simulation system, we typically need 3 main components. First, we need to build a 3D virtual world. This means we need to have geometry representations of both the static background environment, such as the roads and signs, as well as foreground dynamic actors, such as vehicles and pedestrians. Second, we need to generate the scenario we want to simulate in. We need to specify the map and initialize where all the actors are in the scene. Typical actors in self-driving vehicles are vehicles, pedestrians, and cyclists. We then specify the actor dynamics, or how the actor positions and behaviors will evolve over time during the scenario. Finally, we need to leverage both the generated scenario and the virtual world geometry representations to simulate the sensor behaviors for the SDV sensor kit. As discussed in the hardware section of the tutorial, two standard sensors on the SDV are LiDAR and camera. A good closed-loop simulation system will have lightweight geometry representations that capture the essential aspects of the real world, a diverse set of scenarios with human-like traffic behaviors, and fast sensor simulation systems that generate realistic observations of the world that are consistent across different viewpoints, sensor types, and time. Let's begin by discussing how we create the 3D virtual world. We break down the task of virtual world creation into 3 subtasks: background assets that depict the road layout, vegetation, buildings, etc., rigid actor assets that may move during the scenario, such as vehicles and trucks, and deformable assets that change in shape over time, as pedestrians and cyclists do. But first, let's take a step back and ask ourselves, what are the desired properties we would like in our assets for the virtual world? Our assets should have accurate geometry and have high fidelity with the real world assets to enable accurate sensor simulation. And our asset library should also be large and diverse so that our virtual world will allow us for testing of billions of possible unique scenarios. We need to create these assets in a cost-effective manner so that it's feasible to build a large library of them. And we need a compact representation for these assets to easily store and load them. And we also need to be able to render these assets efficiently so that our sensor simulation is fast. And finally, we need to ensure the assets that we have will contain the information needed to simulate the different sensors on our SDV, and that the information is consistent across both sensors. One common approach to building these assets for the virtual world is to have an artist create CAD models for each type of object, specifying their geometry, material properties, and texture. For deformable objects, the artist would also need to specify the necessary components for animation. The benefit of this approach is that we have precise control of the exact type of assets we want to create, and they are high quality and have all the desired properties that we need. The downside is that it is time-consuming and expensive to create these assets. It's also not feasible to generate the wide variety of assets we may observe in the real world and build backgrounds for the millions of different locations we want the SDV to drive in. An alternative is to have vehicles with sensor kits collect data in the different areas we would like to operate in and use computer vision approaches to generate assets from data. This approach scales well and is cost-effective, but requires us to develop methods that are robust to noise and ambiguities that occur during data collection in the wild, such as occlusion, lighting changes, and incomplete observations, and etc. We will now provide an overview of the different approaches used to generate static background meshes, 3D rigid body models, and deformable assets. Let's start with background assets. One straightforward approach to generate background assets is to leverage the LiDAR point clouds collected by the SDV. We record the LiDAR data in an area, remove moving objects using a semantic segmentation model, aggregate and align the LiDAR, combine across multiple trajectories, and create a mesh circle representation. The downside of this approach is that it has noisy meshes, since the segmentation model can be inaccurate, and the LiDAR sensor may have slightly nobler observations, and the aggregation may not be perfect. But the benefits of this approach is that it's simple and scalable, and it has accurate geometry, since every LiDAR point observed becomes directly part of the geometry. Also, one minor note to mention is that we may have holes in our scene if we do not have enough coverage in a particular area. For example, high traffic areas, where we might not see enough of the background. Also, without any further processing, such as simplification, the resulting mesh can be quite large and expensive to store, and therefore also expensive and slow to load and render. To address this large storage limitation and generate a cleaner asset, one can leverage classical surface reconstruction techniques, such as Poisson surface reconstruction, to generate a mesh surface from oriented point clouds. This approach is still simple and scalable, and by leveraging mesh simplification methods, the resulting meshes can be more efficient for rendering. However, This approach can have less accurate geometry compared to surface, especially for non-surface objects like poles and vegetation, and can have blobby artifacts. Additionally, classical methods do not perform scene completion, meaning sparse areas remain incomplete. To address the issues with pole and vegetation, one method proposes to instead construct background assets using a set of primitives, points, edges, and planes. The hybrid representation is generated by performing an energy minimization that tries to fit the primitives to the observation point clouds. This approach preserves geometry well and is compact, but the optimization process can be brittle to noise, and holes remain. One line of work that tries to complete the missing areas is to represent the background scene as a set of neural implicit functions. It builds on the recent work from surface reconstruction methods like DeepSDF and deploys them locally to represent the scene. Applying marching cubes at the desired resolution extracts the final mesh asset. This approach completes the missing areas and can have high resolution, but so far, the results show that the final scenes can still have blobby geometry and artifacts. The past few approaches we have discussed so far have used LiDAR point cloud data to build their background meshes. But to ensure the assets are multi-sensor compatible, we should also be leveraging camera data to store texture information to build these background assets. Different approaches are available to encode RGB information from recorded data into surfaces and meshes, but directly rendering these textured meshes may still not be realistic and have high fidelity. We will see in the sensor simulation section later on how we might handle this. Finally, our recent work at this year's CVPR uses a neural volumetric representation to store a background asset. An MLP encodes the representation, which takes as input a query point and view direction, and outputs a color value and transmittance, which can then be used by a volume rendering algorithm to generate the final image. This approach represents the asset quite realistically in the image space, but has not yet been demonstrated to handle significant viewpoint change. Additionally, the 3D geometry needed for LiDAR may not be accurate, and currently these representations are expensive to render. This is an active area of research, so further progress may help address these issues. We will now transition and review methods used for generating rigid actor assets. The same desirables from before apply, and we will see similar techniques were used for generating these assets, but we also see additional methods that focus on object completion, as moving actors often have fewer observations in the wild. Here's the problem set up for rigid object reconstruction. We typically have a sequence of LiDAR and image data from a single data collection trajectory, and we can use offline perception algorithms or user annotations, such as bounding boxes or segmentation models, to generate only observation data related to the actor of interest. We then want to recover a high quality shape. Similar to background meshes, the first approach we can try is naive surface aggregation. We aggregate the LiDAR point cloud sequence, apply symmetry if we have prior knowledge. For example, vehicles are usually symmetric along their length, and then apply normal estimation and outlier removal to generate the surface mesh. This approach is scalable and allows us to collect a wide variety of vehicles with accurate geometry, but the same limitations for LiDAR aggregation for background meshes still apply. The aggregation can be noisy and incomplete, and the surface representation can be expensive to store and render, if not simplified further. Additionally, the use of symmetry is a heuristic that is not guaranteed to apply. We'd rather learn from data for completing the shape. And shape reconstruction methods using machine learning try to do just that. They try to complete the missing area of the object. One line of work is feed-forward based shape reconstruction methods. Feed-forward approaches directly learn to map the input sensor data to a lane shape representation, which is then decoded into an output mesh. There are feed-forward approaches for point cloud completion, mesh prediction, and SDF completion. Usually, SDF and meshes are denser and have more topology information, making them more desirable. These approaches are usually robust to observations with noise and have a strong shape prior, but they don't always match well to the input observation points. As an aside, when using machine learning for shape reconstruction, we need to be mindful of the ground truth data required for supervision. Here, we present a recent shape reconstruction method that does not require 3D ground truth information, unlike other previous methods that might have used 3D ground truth information via synthetic data to generate the shape reconstruction. We first develop a self-supervised model that takes input from multi-view images in LiDAR, and then predicts per vertex deformations on a learnable mean shape mesh. For self-supervision, a silhouette is differentially rendered from the predicted mesh and compared with the mask labels, and a lighter point cloud consistency loss is also applied. The same strengths and weaknesses apply from before, and the geometry may be coarse. Here are some additional visualizations of the reconstructed assets with source image crops of the vehicles warped to the target views. Despite the smooth and coarser geometry, the resulting assets still look realistic. Another way to tackle shape reconstruction is to leverage optimization algorithms that fit an object representation to the sensor observations. Deep optimization-based approaches generally deploy an auto-decoder framework, where a latent code or network is iteratively optimized at test time according to sensor data, ensuring high fidelity with the input observations. However, these approaches do not perform well on in-the-wild real data, as the optimization is usually based on a handcrafted objective function and can generate latent codes that are out of distribution, producing bad output shapes. There's also no global shape prior to ensure shape realism. A recent work from our group combines both feed-forward approaches and deep optimization approaches to gain both of their benefits while addressing each other's deficiencies. We first adopt the encoder module from the feed-forward approaches, which acts as a robust initialization of the latent code. Next, from deep optimization approaches, we perform test optimization of this latent code. And to ensure global shape consistency, we introduce a discriminator module to have global shape prior. This approach has high fidelity with input data and strong shape prior, and can leverage both sensors. And this approach works well compared to existing methods on in-the-wild real data. But this method and other shape reconstruction algorithms usually leverage only a single frame of data instead of the full sequence. It's still an open area of research to further push progress to achieve the desired properties for rigid body assets. And so now I'll pass it on to Ze to discuss building deformable animation assets. Thank you.
Thanks, Siva. Hi, my name is Ze, and I'm a research scientist at YB. Next, we will cover how we can create deformable objects. We focus on pedestrian because this is the most common rigid object in urban setting. Given an input camera image and a sparse LiDAR point cloud captured by sensors, we aim to reconstruct the object shape and its deformation model. Then we can reanimate the shape and place it into new scenario. However, recovering pedestrian is not easy because they are diverse and their shapes are deforming over time. So we cannot directly aggregate partial LiDAR scan to obtain the full shape like for vehicle. Now we talk about methods to reconstruct human shape. Methods can be divided into model-based approach, model-free approach, and mixed approach. We will briefly summarize each approach. We first look at model-based approach. This method usually fits parametric human model to input observations. Recent works usually use simple as the human model. The model-based approach guarantees never missing body parts, and the human model is differentiable and easy to use. However, the reconstructed shape cannot represent fine-grained details and clothing because the shape space is constrained by the human model, and the reconstructed shape is not guaranteed to align well with pixels. Next, we look at the model-free approach. We first look at the silhouette-based approach. They usually predict 2D silhouettes from multiple viewpoints based on input observations. Then, visual Hall or Kelvin algorithm was performed to extract the shape from multi-view silhouette. These methods usually generate human mesh that aligns better with pixels, but the estimation is not good at concave regions, and the results are prone to silhouette error and sparse views. The next model-free approach is barometric-based approach. They usually predict the voxel rotation of a human from input observations using deep neural networks. The predicted shape usually aligns well with input image. However, voxel rotation is computationally costly, and it is a coarse rotation. Recently, some papers use implicit rotation to represent the human shape. Then it performs matching cube to find the underlying human mesh. This line of works can reconstruct fine-grained details and clothing. The limitation is that not all body parts are guaranteed to have been reconstructed due to depth ambiguity. Next, we look at the mixed approach for shape reconstruction. Some papers extend the parametric human model with a vertex deformation, so they have the potential to extend the shape space, but they still cannot adapt wear to heavy clothing and accessories because the mesh is constrained to a fixed topology. Some other papers land human shape on canonical UV space defined by a simple model. They formulate the shape reconstruction problem into an image-to-image translation problem. This approach usually reconstructs high-resolution textured shape, but it requires the input mesh to have the same topology and a canonical UV space, which limits its sterilization ability. After reconstructing the human shape, let's look at how we animate the shape. We first look at the parametric human model. The most simple model is blend skinning model. The idea is to softly assign each vertex to human bones with skinning weights. The skinning weight measures how the vertex deforms as pose change. And the skinning model are simple to use, but they cannot model the shape change between different people, and they require human designers to design the whole model, which is tedious and does not scale. Simple is the most widely used parametric human model in recent years. They are much powerful than linear blend skinning model because they introduce identity-driven shape deformation and post-blend shape. However, it's constrained to liquid human shape. The garment composition approach extends the simple shape space to model clothing human. They usually learn a garment layer on top of the parametric human model. This approach usually have a higher level of control compared to reconstruct a single layer mesh. However, they require high definition input scan or some garment prototypes, and the methods cannot generate wear to real image. Finally, we look at methods based on shape learning plus parametric human model. This approach usually uses implicit fields to learn human shape due to its superior performance. Some works learn human shape first and then register simple model to reconstruct the human shape. Some other approach estimate simple models to input observation first and then learn implicit fields on top of it. This line of work can recover animated models with fine-grained details and clothing. However, they cannot adapt wear to lower topology because they reuse animation components from predefined simple model. All of the existing approach reuse the skinning weights from simple. However, simple definition is not optimal for all human shape, especially the heavy clothed human. Also, there might be error propagation in staged pipeline. Different from this approach, we don't use the skinning weights from a predefined simple model, but instead, we directly learn it from data. We learn S-cubed fields, stands for shape field, skeleton fields, and skinning fields, to directly predict an animation-ready model. Our predicted model consists of a mesh, a skeleton, and a skinning weights. This example shows the reconstruction animation results on real data captured from urban scenes. We reanimate a working man to perform different actions. Our model reasonably handles the shape deformation for a closed human and works well even for animations that have never seen before. It's also critical that our approach works across all gender, skin colors, body types, and clothing. Here we reanimate a jogging woman to kick a ball, breakdance, and perform other interesting unseen animations. The animated mesh deforms realistically to those lower poses. Next, we present how we infer the skinning weights, shape occupancy, and the skeleton probability for arbitrary query points in continuous 3D space. We first process sensor observations to feature map. Then we project the query points into a feature map and interpolate the local feature. Additionally, we concatenate local feature with a viewpoint feature to obtain the point encoding. Finally, we feed the point encoding to task-specific MLPs to generate the skinning weights, shape occupancy value, and the skeleton probability at the query point location. Now, given a length S-cubed fields, how do we infer the human animation model? We first construct a dense grid of query points according to our designed resolution, and then we evaluate neural S-cubed fields. We then post-process them to obtain the underlying human mesh, skeleton, and the skinning weights, which can be then used for reanimation. To train the network, We adaptively sample query points to effectively learn each field. We infer the neural SQ value on the sample points and compute loss to train our network. Next, we show surface reconstruction results on real-world data. Notice our model accurately predicts the human shape even with the large and puffy jacket. Our shape is more realistic looking than simple-based methods. We're having fewer artifacts than PyFu and PyFu-HD. By zooming, you can see our model reconstructs better global topology and local details. We can better handle the additional shoulder bag in the scene, while simple-based approach lack details, and PyFu and PyFu-HD can load separate arms and back. Here's another example. Notice we're able to reconstruct a woman's jeans wear compared to other methods. We're also having no holes or merged body parts. And here is a closer look. We're better at handling the fine details, such as hand shape and arm pose. Finally, we show reconstruction and animation results on real data captured from urban scenes. For each example, we first showed input camera image and the reconstructed skeleton and mesh. We then showed the reanimated mesh at a target pose. Our approach reconstructs and animates a wide variety of humans with different shape and with different clothing, such as caps and coats. Next, I will move it to Kevin to discuss how to generate traffic scenarios for closed-loop simulation.
Hi, my name is Kelvin. I'm a researcher at Wabi. Next, let's discuss how to generate traffic scenarios for closed-loop simulation. A standard approach for scenario generation is to manually specify scenarios from scratch. This can be done using a domain-specific language like OpenScenario, or we can use a simple GUI to directly drag and drop actors onto the scene and draw trajectories for them to follow. Manual scripting is extensively used across the industry since it allows us to precisely test specific SDB capabilities. However, scripted scenarios are usually non-reactive since actors follow fixed predefined trajectories. This limits realism since, for example, an actor might rear-end a slow SDB even though it would have avoided the collision in the real world. Moreover, manual scripting requires significant human efforts, and as a result, it cannot scale to capture the full diversity of real-world traffic scenes. To better capture the breadth of real-world scenarios, we can instead extract scenarios from real-world driving logs and then generate random variations of them using a technique called fuzzing. This approach can give us large collections of realistic scenarios that we can scale by simply collecting more data. However, like scripted scenarios, these extracted scenarios are non-reactive. Furthermore, this approach limits us to testing within the neighborhood of scenarios that we've observed in the real world, which may be insufficient for testing rare or safety-critical cases. Therefore, in order to scalably test our self-driving vehicles in simulation, we need methods that allow us to automatically generate scenarios that are both realistic and diverse. And in particular, given a high-definition map of the scene and an initial configuration for the self-driving vehicle, we'd like to first initialize the scene with actors of varying classes and attributes. And then we want to simulate their behaviors over the duration of the scenario in a reactive manner. I will first present an overview of some methods for generating the initial scene. Later, my colleague Simon will discuss how we can simulate actor behaviors as well. So let's get started. A very simple approach to initial scene generation is to use simple heuristics. For example, we can specify how many vehicles we want and then place those vehicles at predefined spawn locations. Although easy to implement, this approach is far too simple to capture the diversity of real-world data. Furthermore, it can be difficult to design good heuristics that generate realistic traffic scenes. A more realistic approach is to use rule-based generation to insert actors into the scene according to its road topology. For example, given a lane graph of the scene, we can insert vehicles in the middle of each lane according to a set of rules that govern things like minimum bumper-to-bumper distance between two vehicles or their minimum time to collision. In addition, we can also sample concrete values for these rule parameters from a simple learned model. This approach is partially data-driven and allows us to encode constraints in the generation rules. However, it typically handles a limited number of lane topologies and actor types only, and it uses rules that are generally far too rigid or models that are far too naive to capture the diversity of real-world scenes. To better leverage data for traffic scene generation, a more recent line of work marries deep generative modeling with probabilistic scene grammars to generate scene graphs. Here, a scene graph is a hierarchical representation of a scene, where each node is an element in the scene parameterized by some set of attributes. For example, a car would be a child node of a lane node, reflecting the relationship that cars are generally placed on top of lanes. In Medicine 1, the authors trained a distribution transformer to generate realistic scene attributes, such as vehicle type, color, etc. And in Medicine 2, the authors trained a model to generate the structure of the scene graph as well. This approach allows us to generate structured scene representations that can be easily used in downstream simulation modules. Furthermore, the generative models used here can be directly optimized for some end task, such as to improve the performance of a perception model trained using this synthetic data. However, this approach still requires designing a good scene grammar, which is challenging to do and may limit our ability to capture the diversity of real-world data. To sidestep the challenges of designing realistic rules or scene grammars, SimNet proposes a fully data-driven approach instead. And in particular, SimNet uses a conditional GAN to perform image-to-image translation from a rasterized image of an empty traffic scene to one that has been populated with actors. SimNet removes the need for rules or scene grammars, allowing us to more flexibly model the breadth of possible traffic scenes in the real world. However, it generates an unstructured representation, so we must use heuristic post-processing to extract actors from the generated images. And unfortunately, these heuristics can be unreliable or challenging to tune, especially if the generated scenes are unrealistic at times. Building on these past approaches, SceneGen is a recent work from our lab that learns a neural autoregressive model of traffic scenes from real-world data. The way it works is by composing a scene by iteratively sampling new actors and inserting them into the scene one at a time. Unlike the previous approaches, SceneGen is fully data-driven, generates a structured output representation, and requires no handcrafted rules or heuristics. This allows us to better capture the diversity of real-world traffic scenes in a way that scales with data. One weakness of this approach is that we may sometimes get unrealistic samples from the model's unreliable long tail. However, since SceneGen admits a tractable likelihood function, we can easily find and reject such low probability, unreliable samples. Furthermore, we can also modify the sampling process to enforce constraints such as no collision. Next, let's take a look at some samples from SceneGen. Here we're visualizing the autoregressive generation process, which we've slowed down for visualization purposes. The SDV is shown in red, vehicles in blue, pedestrians in orange, and bicycles in green. We can see that samples from SceneGen are quite realistic, and we can sample from this model over and over again to generate as many scenes as we want. This wraps up our brief overview of traffic scene generation. Next, I'll pass it over to Simon, who will lead our discussion on the next piece of the puzzle, how to simulate actor behaviors.
Thanks, Calvin, for your great introduction to scenario generation. Hi, everyone. My name is Simon, and I'm also a research scientist at Wabi. I'm super excited to talk about the next step in the scenario generation process, simulating the actor behaviors. Before diving into the approaches, let's talk briefly about the desired characteristic of an actor simulation. First of all, in order to generate realistic scenarios, we need to capture naturalistic behaviors and complex interactions that humans exhibit in the real world. Secondly, to generate diverse and interesting scenarios, we need to sample different variations given an initial scene. And lastly, this process needs to be computationally efficient such that we can effectively scale our closed-loop simulator. Now, understanding and replicating human behavior is a key theme in both autonomy development and simulation. But there are some key differences between the requirements in actor simulation and those in prediction and motion planning. In motion planning, the goal is to generate the safest and optimal trajectory plan. Even though we may learn by imitating human driving, we're interested in learning only the best driving behavior. This is illustrated below by the single red trajectory that safely follows the lead vehicle. Whereas in actor simulation, we're interested in recovering the full distribution over human behaviors, which includes potentially reckless and dangerous maneuvers.
Good afternoon. My name is Siva, and I'm a researcher at Wabi. In this session, we will be discussing an important behind.
Sorry, Siva. Can you have a check of what's the video it plays?
Yeah, I think it's probably like around the 35-minute mark.
Remain here is to infer the actions, and then directly comply with clear information about which includes the human exhibit.
Yeah.
Yeah, here, right?
A bit more, yeah.
A bit more.
Yeah, somewhere here, I think.
Cool. Sorry for the mistake.
Trajectory plan. Even though we may learn by imitating human driving, we're interested in learning only the best driving behavior. This is illustrated below by the single red trajectory that safely follows the lead vehicle. Whereas in actor simulation, we're interested in recovering the full distribution over human behaviors, which includes potentially reckless and dangerous maneuvers. This is illustrated by the distribution in orange, which includes aggressive lane changes. Now, let's compare actor simulation to the prediction task. In prediction, we aim to infer future actor behavior from partial and noisy sensor observation while being uncertain about their goals and intentions. For actor simulation, we may assume perfect information about the environment and other actors, and also specify their desired goals and intentions. This gives us an additional degree of control to centrally coordinate actors for creating desired scenarios. Another key distinction is that actor simulation is a closed-loop task where previous actions influence the future states experienced by the actor. This creates a unique challenge in learning from observational data, which we will discuss in detail later. The simplest approach to automatically generate actor behaviors is using rule-based models. A typical car-following model describes a simple set of vehicle dynamics that follows the lane and maintains the desired clearance from the lead vehicle. This can be extended to generate lane change behaviors as well, using yet another set of rules, such as the gap acceptance model. While these rule-based models are simple and can guarantee actor behaviors that are traffic rule compliant and collision-free, they're rigid and just a little bit too perfect. As a fellow human, we all know simple lane following is a gross simplification of what actually happens in the world. In order to prepare our autonomy system for the real world, we need to simulate the long tail of actor behaviors, which includes non-compliant behaviors such as cutting corners and turning U-turns, different actor behavior styles such as aggressiveness and cautiousness, and finally, complex interactions such as yielding and merging, all of which are difficult to explicitly model with rules or heuristic. And as a result, learning from data may be the only scalable solution. The simplest way to learn from data is behavior cloning. Basically, we will collect an offline data set of state action pairs and then directly train a policy with supervised learning. This is essentially the same process as learning a prediction model, and it has the benefit of being simple, scales with data, and has been shown to work quite well for short time horizons. However, it is generally not robust when unrolled for longer time horizons due to compounding error. This is because the policy only observes ground truth states during training, but encounters novel suboptimal states when unrolled in simulation and fails to recover. SimNet is a recent paper that actually uses vanilla behavior cloning for learning reactive simulations. It attempts to mitigate a compounding error problem by simply training on a ton of data. As seen in the video, after training on 1,000 hours of driving data, the model learns convincing reactive behavior. Another data-centric solution to the behavior cloning problem is data augmentation, where we expand expert distribution with out-of-distribution states and corresponding desired actions for recovery. In this paradigm, the learning procedure remains simple and familiar since it's still a supervised learning task. Now, optimally, we will like to query an interactive expert, but that is often unavailable or prohibitively expensive. Other methods seek to heuristically generate more synthetic examples to cover this space, but this requires manual design which could be brittle and adds bias. A learning-centric solution is to actually add auxiliary losses and thereby regularizing the policy to avoid these bad states to begin with. This could take the form of manually designing traffic rule losses that penalize lane violation and collisions, or even learn uncertainty model that penalize the policy for arriving at auto-distribution states. While these methods help capture common sense about driving, they may impose too strong of a constraint to learn naturalistic and diverse behaviors. Another alternative paradigm to policy learning is cost learning. The high-level idea here is to infer the costs associated with state action pairs instead of directly learning the policy. Then, after learning these policy costs, one can use any planning approach to solve the task. These methods have the benefit of allowing us to incorporate domain prior knowledge via the flexible cost functions we design. However, they require an additional optimization step as compared to directly learning the policy. A closely related approach that takes it one step further is adversarial imitation learning, which proposes to learn a discriminator to distinguish expert rollouts from policy rollouts. And then the policy is learned jointly to fool the discriminator in a Gantt-style alternating optimization. Now, furthermore, the discriminator can also be leveraged as simulation time to prune out bad rollouts in a post-processing step. While this approach cleanly avoids the behavior cloning issues without manual data augmentation or auxiliary loss, it could empirically be very difficult to train due to the joint optimization over policy and discriminator. Furthermore, it requires a large amount of policy on roll for learning. Lastly, I'm beyond excited to share the latest work from our lab, Traffic Sim. In this work, the key focus is to model all actors in the scene jointly, which then allow us to capture complex interaction between actors that we observe in the data. To this end, we leverage a graph neural network-based latent variable model, which is shown on the top right, that can generate inconsistent trajectories for all actors. This also gives us the ability to generate scenario variants given an initial scene. Furthermore, in contrast to the vanilla behavior cloning, we unroll the policy to observe simulated states induced by the policy and backpropagate through a fully differentiable simulation across time for learning. And we've seen that it's very effective in mitigating the behavior cloning problem. Our model is able to handle a large number of actors in the scene and is adaptable to a wide variety of map topologies. Furthermore, our models is efficient and allow us to generate a large number of scenarios scalably. Now let's take a look at a couple of actors in detail. In this first example, the actor nudges past a parked vehicle partially obstructing its lane. Here, the actor first yields for oncoming traffic, then performs a U-turn. In this scenario, the actor slows down for a parked vehicle ahead, then waits for a nearby actor to pass, and finally lane change to make progress. In this last scenario, the actor yields for oncoming traffic before performing an unprotected left turn at an intersection. Learning-based scenario generation remains a relatively underexplored field with many exciting frontiers. Most existing work has thus far focused on learning unconditioned policy, where we can only sample possible actions from the policy without the ability to control the actors individually or the scenario as a whole. Learning controllable actor behavior and interactions will be critical to enable targeted evaluation of autonomy capabilities and will further transform the autonomy evaluation landscape. And we could take this step one step further. We could take this idea one step further and look towards automatically discovering and generating adversarial scenarios to test the limit of the autonomy system. We will touch on this topic more in the next module. And lastly, it remains challenging to succinctly define the goals of the actor simulation task. Right now, existing work leverages pseudometrics ranging from scenario reconstruction error, traffic rule violation rate, to reactivity score to evaluate a simulation. More work needs to be done to explicitly evaluate a model's ability to capture the long tail of interesting human behaviors and interactions instead of just the average case. Now, I will pass it over to Siva to discuss sensor simulation.
Thanks, Simon. So we finished discussing virtual world creation and scenario generation. We now need to simulate the sensor observations for a given traffic scenario. While there are a suite of different sensors that can be helpful on the self-driving car, such as LiDAR, camera, radar, IMU, and so on, we focus discussion in this tutorial to LiDAR and camera, as they are the sensors most prevalent in the self-driving industry. Sensor simulation of LiDAR and camera data is a challenging topic. For an end-to-end closed-loop simulation system, we have several desirable properties that we want in our sensor simulation. First, it should be highly realistic, especially as viewed by the autonomy system. Additionally, it should have close to real-time rendering performance for fast execution, should be consistent across sensors and viewpoints, and temporally consistent. Many of the properties that we saw for the virtual world asset creation reappear for sensor simulation, as they are tightly coupled. We'll now cover approaches for LiDAR simulation. First, let's take a look at a LiDAR sensor on a self-driving vehicle. A LiDAR sensor generates 3D point clouds that represent the geometry of the scene, and can also contain information about the material reflectance about the object it hit, which we call intensity. As reviewed in the hardware section, the basic mechanism for how a LiDAR sensor works is as follows. First, a laser shoots a pulse of light at high power in a particular direction at a precise point in time. The light beam hits an object, and the light is dispersed in different directions due to a variety of factors, such as the atmosphere transmittance, the incidence angle of the intersection, the material properties, and so on. But some portion of the light returns to the LiDAR sensor, and the sensor monitors the received power over this brief duration in time to generate a LiDAR waveform. We can apply post-processing to identify the peak in the signal, and then measure the travel time for the recorded peak to determine an object's distance. If no peak is extracted, then no LiDAR point is returned. Now, while the LiDAR laser pulse is quite precise, as it travels further away from the sensor, the laser beam can grow in size, which is called beam divergence. Any fraction of light in that beam that returns to the sensor above the threshold can be recorded as a hit, which can therefore called noise in the point cloud. Additionally, when a spinning LiDAR is mounted on the self-driving vehicle, two special effects occur that we should take into account during LiDAR simulation. Rolling shutter occurs when the ego vehicle moves during the rotation of the LiDAR sensor, creating a discontinuity in the sweep. Motion blur occurs when another actor is moving during the rotation of the LiDAR sensor, making the actor appear distorted in the point cloud. These are important effects to simulate to ensure proper timing in the LiDAR point cloud observation. We now review approaches. One standard way to simulate the LiDAR sensor is to use a physics engine to compose the virtual world assets into the scene, and then perform primary raycasting according to the LiDAR sensor configuration to generate the simulated point cloud. This allows full scene control and is reasonably simple and fast, but the simulated LiDAR can look unrealistic in the sense that it does not have noise and can be denser than the real LiDAR, since it assumes all the rays casted come back to the sensor. One reason why the previous LiDAR simulation approach is unrealistic is that the game engine simulators don't properly model the LiDAR physics, such as the material reflectance properties, or use the specific calibrations of the different LiDAR sensors. Enhanced graphics engines attempt to apply geometry noise and drop points from the point cloud based on additional information, such as recorded distance and the material properties. Unfortunately, enhanced graphics suffers more so from the previous issues mentioned before, with the additional disadvantage that the simulation can be slow. The BlendSort engine requires a single LiDAR sweep to take about 8 to 9 seconds of frame to generate, preventing scalable autonomy testing. One challenge with the enhanced graphics models like BlendSort is that it requires detailed information about the scene's material properties and sensor calibration information to simulate the LiDAR. A recent paper presents a LiDAR simulation approach that leverages real-world data with a differentiable enhanced physics renderer to render the full LiDAR waveform for a given simplified scene. Through backpropagation, it can estimate the parameters of the scene, such as material reflectivity and the sensor's pose, to ensure that the simulated LiDAR waveform matches well with the real LiDAR waveform. This approach shows promise, but is yet to be demonstrated in a self-driving setting with complex scenes, and it's unclear if the learned properties will transfer across scenes. Additionally, similar to Bunsen, this approach, while physically accurate, may be computationally expensive. Another approach to LiDAR simulation is to not use raycasting at all, and instead use a data-driven generative model that takes a latent code as input, which represents the scene, and directly outputs the final point cloud. This approach is fast and gains a nice prior based on learning from real data, but there's no semantic control of the scene, and the point cloud generation is usually for a fixed size, and it's not a multi-view or temporally consistent approach. And additionally, the resulting point cloud can be overly smooth and have artifacts. An approach from our lab is LiDAR Sim, which builds on the past work by incorporating both graphics and data-driven approaches, along with machine learning. LiDAR Sim uses a physics engine to compose a scene, performs primary raycasting based on the sensor's calibration to generate the initial point cloud, and then uses machine learning to drop LiDAR points to make it appear more realistic. Since LiDAR Sim builds assets from real-world data, we can leverage this information contained in these assets to improve the network's predictions of ray drop. This approach combines the best of both techniques, using our prior knowledge of the basic physics to generate the initial rendering, while applying machine learning to handle the higher order physics. We can see in the bottom figure that using machine learning makes the simulated point cloud better match the real one. The disadvantage of this approach is that it may not generalize well to unseen objects, and the ray drop network would probably need to be retrained if we want to simulate a different type of LiDAR sensor. Let's go into more detail about how LiDAR Sim works. Given a virtual city, we first perform raycasting to generate the initial LiDAR point cloud. But however, raycasting generates more returns than the real LiDAR typically, because we return the points no matter whether or not the intersection would have caused a signal in the real world, because they may not meet the detection threshold in the real LiDAR. This ray drop phenomenon is complicated to simulate by physics alone, because we don't know the physical parameters of our real world, such as the material properties and incidence angles. However, since we build our assets from real data, we can leverage this information along with the ray drop network to bridge the sim to real gap. We first convert each raycasted LiDAR sweep into a spherical image representation, encoding features related to ray drop, such as the range values, incidence angles, semantics, and path intensity values. We then feed these features into a network and predict how likely a ray will be dropped. The labels that we get come from real LiDAR ray drop patterns. We sample the ray drop probability to generate the final point cloud. We now show some qualitative results. This side-by-side comparison shows that LiDAR Sim generates realistic point clouds with small domain gap for downstream perception tasks and autonomy testing. The green detection bounding boxes are from a perception model trained on real data only. And we can see that the boxes appear and disappear in both the simulated LiDAR and real LiDAR at about the same time. With LiDAR Sim, we also can now evaluate a perception and motion planning system maneuvering safety critical scenarios in a closed loop setting. Here we see a simulated scenario where a vehicle turns into the SDV's lane, occluded by a bus. The system, trained only on real LiDAR data, is able to process the LiDAR Sim data and safely brake to avoid collision. And so with no additional training or domain adaptation, we can directly use LiDAR Sim to test an autonomy system end-to-end on millions of different scenario variations, achieving results that match closely with the real world and allowing us to gain new insights. I'll now pass it on to Shenlong, who will now.
Thank you, Siva. My name is Shenlong, and I'm an incoming assistant professor at UIUC. I'm going to deliver a tutorial on camera simulation. Along with LiDAR, the camera sensor is another critical component for the self-driving cars. And as we learned previously in hardware session of the tutorial, modern autonomous driving car platforms are equipped with multiple high-resolution cameras covering different viewpoints from the sensor. This means that for camera simulation, we need to simulate camera images which are consistent across space and time. There are many works in the computer vision and robotics community that address the camera simulation for self-driving. Some approaches tackle the full camera simulation problem, which involves rendering a scene representation with actors from the camera viewpoint on the ego vehicle. Others break down the problem into two subtasks: novel view synthesis, where the task is to render the camera images at an ego vehicle's new location given a scene representation, and a dynamic actor insertion and removal, where the task is to remove or insert actors into the scene and generate an updated camera image for the new scene. By combining novel view synthesis with dynamic actor insertion and removal, one can attain the same capacities as full camera simulation. Let's now discuss the different approaches taken to solve the full camera simulation problem. Similar to what we saw in the LiDAR simulation overview, we can use the physics game engine such as Scala or GTA to firstly compose a scene with post-virtual assets, and then apply standard graphics engine to render the final image. Typically, the virtual assets are created by artists and then annotated with textures or material properties such as albedo, shading, metallic, and glossy for the rendering engine to account for lighting effects. Like before, we have the full control of the scene and can render from multiple viewpoints. Also, the renderings will be temporally consistent as the same assets are used throughout the simulation, and the physics engine will update the asset's location. However, high-quality photorealistic ray tracing or recasting, such as in the movies, is extremely computationally expensive and not real-time, while traditional rasterization-based pipeline is far away from being photorealistic. Additionally, using the standard graphics alone means that there are significant constraints on the types of assets required to achieve realism and may require manual efforts. This means that such an approach is not automatic and may not scale to millions of locations that we may want to evaluate autonomy in. So instead of using the standard graphics-based approaches, one can leverage image translation neural networks to generate a camera image. Works such as Pix2Pix takes a semantic annotation as input and directly predicts the final image. This generation process is fast and fully automatic, but placing all the image generation burden on the 2D network side means that it is very hard to encode 3D information easily. That means these approaches are not multi-view or temporal consistent. Additionally, using neural network to generate complex urban scene images can have visual artifacts. And while this approach is automatic and fast, the input segmentation can be hard to generate. It may require game engine to render those images or manually annotate those real images. To address the limitation that image translation method lacks 3D information, a recent approach, work consistent V2V, tries to incorporate depth information to improve the image quality. As before, work consistent V2V takes a semantic segmentation image as input, but also leverage structure for motion to generate a 3D estimate of the scene as a point cloud. This 3D representation is rendered into the target view as guidance image in addition to semantics. The use of guidance image makes the approach more 3D aware and multi-view consistent, while still remaining fast. But this approach still has artifacts and not proven to be useful for training and validation for self-driving autonomy. So rather than using the just semantic segmentation as input and translation network, recent work attempts to leverage standard graphics engines to render an initial camera image. This camera rendered image, along with other game engine generated inputs, such as the G buffer, like the depth or semantics, and the surface materials, can then be used to a translation network to enhance the photorealism of the image. Using both graphics and image translation allows the method to share the rendering burden and gaining the benefits for both. In addition, image translation methods can be used to generalize the rendered image to different weather conditions or geographic domains. However, the same constraints on the assets and difficulties in scaling remains when we use a graphics engine to render the initial image. Since we now use both graphics and machine learning to perform rendering, some methods have tried to reduce the constraints on the assets requirement as the cost of having a lower quality initial graphics rendered image. Surfogam generates textured assets from the real data, then perform recasting to generate an initial image. This image can be then improved by matching the style of the real image using a neural network, and this approach scales well, while still maintaining the full control of the scene and multi-view consistency. However, the use of the surfo-generated assets means that the generated images have lower resolution. Recent work such as stable view synthesis try to improve performance by rendering the feature space and then using neural network to generate the final image, but has yet to be extended to dynamic autonomous driving environment. Finding the right balance of model-based or physical-based graphics and machine learning is still an open area of research. The previous approaches discussed using either graphics-based approaches or image translation methods, or a combination of the two. Another approach of full camera scene via a fully generative networks that takes a latent code as input and generate a final image. The latent code can be disentangled to be conductive to semantic manipulation and can be also updated by a dynamic engine to maintain the temporal consistency. This approach has similar strengths and weaknesses to the image translation. It's automatic and fast, but it is not 3D aware, and the images can somewhat low quality. So instead of using a single latent code to directly generate the final image in 2D space, recent approaches leverages exciting work happening in the neural radiance fields, or NeRF. NeRF methods perform neural volume rendering with MLPs, where the MLP itself encodes the assets or scene representation, and then graphics-based methods such as volume rendering query the NeRF networks based on the input position coordinate and view direction, and generate the final image. Here we show the qualitative results from the neural scene graphs, which show high-quality results on KT dataset. Their approach of making NeRF representation per asset makes the scene more composable. This approach is also quite photorealistic, but can be expensive to train and render. Recent methods such as neural sparse voxel fields try to improve rendering speed. There are still open directions in this line of work, such as better handling the new views or assets completion for unseen areas. The final full camera simulation approach we'll discuss are recent works at this year's CVPR that combines both neural volume rendering and image translation together. A scene is firstly composed of NeRF MLPs, and then volume rendering is performed to generate an initial 2D image in the feature space. Here, the volume rendering outputs feature vectors for each pixel instead of the RGB values. Then a final image translation network transforms the dense feature map into the RGB image. The results looks nice and temporally consistent, but have yet to be demonstrated to handle dynamic urban driving scenes. So the approaches we just covered perform full camera simulation. As mentioned previously, we can also decompose camera simulation into two subtasks: novel view synthesis and dynamic actor insertion and removal. Some of the methods from the full camera simulation cover these tasks as well, but I will discuss now the methods specific to these subtasks. For novel view synthesis, Some recent approaches leverage databases of existing log trajectories of the real-world data to generate new views. Given a new eagle view location, we query the database to identify a source image. A depth prediction network generates the depth of further image, which is used to warp the new image to the target view. Any remaining holes can be impinted and by bilinear interpolation or image impinting networks. A critical component of these approaches is accurate depth information to perform image warp. But if good depth is obtained, the result is efficient, scalable, and very realistic since it leverages the real-world appearance. However, it cannot handle large viewpoint difference and deviations from the original trajectory, such as lane changes. By itself, it cannot handle modification to the environment, but style transfer network may be used to enhance the image. We'll now talk about actor insertion and removal components of the camera simulation. A similar approach to what we saw for novel view synthesis can be applied to dynamic actor removal. This work leverages a large dataset of video trajectories with accurate depths from LiDAR and image data from cameras. It constructs a 3D scene with the LiDAR point clouds, which allows for view warping of the images from different locations and videos to the target scene, which can then be blended together to create impinted results. There are also other many works on the image impinting that I will not cover today, but I just wanted to briefly cover this task to show how a full camera simulation system can be created from these subtasks. We'll now discuss recent works on actor insertion. Recent works take an existing semantic segmentation map, samples the new location, and the bounding box in the scene either randomly with a learned prior, and then use a network to add the semantic segmentation to the map. An image translation network is then used to render an output image. The image segment for just the generated region can be blended with the real image for the final results. This approach is fully automatic, but suffers from the same challenge as image translation method. It is not so 3D aware since the sampling is in 2D, and it might not be temporally consistent since the network does per frame predictions. It also still requires a real image and corresponding annotated semantic segmentation. Other recent works on improving dynamic actor insertion leverages the real-world data along with standard graphics. Given a real-world background image, a new location and a pose in 3D is sampled to place the actor in the scene. A graphics engine renders the insert assets at the pose, potentially with the environment lighting maps, to generate the image segment to be inserted. The two images are blended together to create the final image for the updated scene. This approach has a strength that rendering is done in 3D, so it can be multi-view consistent, but previous works may require manual interventions for actor placement. Instead of using standard graphics, other methods you may use generative models to insert the actor into the scene, where the actor is represented as a latent code. Depending on the generative model, the inserted image segment may have visual artifacts and may not have good multi-view or temporal consistency. Similar to full simulation approaches, a good balance of leveraging both real data and standard graphics and machine learning can generate high-quality results. Here we present a method at this year's CVPR, GeoSim. GeoSim firstly reconstructs 3D assets from the real-world data and then inserts the dynamic objects into the video sequence. The results are realistic, geometrically consistent, traffic-aware, and scalable, but it does not handle explicitly illumination in this approach. We now show how GeoSim leverages assets library discussed previously in the assets creation section to insert vehicles and simulate new videos. We firstly automatically generate a plausible placement and trajectory that complies with existing traffic of the current scenario. A asset with a similar viewpoint is selected for rendering. We then render the selected assets as a new target pose. We account for occlusion by using dense depths from a pre-trained depth completion network. In addition, since our assets are 3D, we can render them inside graphics engines to obtain soft shadows. And finally, we perform post-image composition. We use a synthesis network to handle inconsistent illumination and append the discrepancies at the boundary so that the vehicle fits in seamlessly. Here is an example of our approach applied to video simulation. Notice that our simulated objects are temporally coherent and the added vehicle obey traffic and have reasonable motion. And unlike 2D-based approaches, we can simulate consistently across reasonably long time horizons. Notice that the vehicle in front. GeoSim retrieval-based approach from the real data allows us to simulate different appearance, like these flashing braking lights. Notice that this scenario, the simulated vehicles are running the red light, creating an interesting scenario with a police car. Being 3D aware also means that we can do multi-camera simulation that is physically plausible. Here is a top view that shows one of the side cameras, while the bottom view shows the front-facing camera. The 4 vehicles simulated by GeoSim are consistent across different cameras. And here are some additional qualitative examples. Can you determine which vehicles are simulated? The answer is here. GeoSim can simulate diverse scenarios such as different viewpoints while handling occlusion from static background and construction, other vehicles, and even pedestrians. For existing camera simulation approaches, one can easily detect the added objects due to the geometrically invalid results, smear cars, or unrealistic appearance. But GeoSim images are hard to distinguish from real. In a human study, users heavily prefer our method over existing approaches. Additionally, our hybrid geometric guided warping method significantly outperforms other rendering options such as graphics-based options or 2D image synthesis methods. So in summary, full autonomy testing and training means that we need multiple components. To build such complete simulation system, we need to animate the dynamic state of the environment, where we have actors, including vehicles, pedestrians, cyclists, construct geometry of both static environment and the dynamic actors, and finally simulate the sensor observation of the self-driving vehicles received. We are very excited about the simulation. There is a lot of exciting areas for the community to explore, simulating all kinds of sensors, or building the world and automatically training and testing. And thanks for listening.
Cool. So that was a kind of a long one, but if anyone has any questions on simulation, happy to take them now. And then around 4 o'clock, we'll start with adversarial ML. Cool. We'll go ahead and get started with the next one.
Hi everyone, I'm James and I'm a research scientist at Wabi. Together with Jinkong, we'll be talking about adversarial robustness in self-driving. As autonomy systems continue to improve, they pass more and more tests, saturating performance on standard benchmarks. However, do these tests cover everything that might happen? Benchmark datasets don't necessarily test capabilities in safety-critical scenarios. So we need tools to automatically generate worst-case scenarios. As we've seen previously in the self-driving tutorial, the stack is composed of a few modules. First, we perceive the world with object detection to identify our surroundings. Next, we perform motion forecasting to understand the actions of the actors. Finally, with our estimation of the future, we can plan our own trajectory to reach the goal while driving safely. Given the modular nature of the stack, we can test each component separately. For example, we can create challenging examples for the perception module. Similarly, it's also important to test safety-critical scenarios to test the capabilities of the motion planner. And finally, the most holistic way is to test the entire stack end-to-end, starting from sensor simulation and all the way to motion planning trajectories. To generate these challenging scenarios, we'll leverage adversarial attacks. So let's dive deeper into adversarial attacks, as well as their applications in self-driving. First, we'll provide some background on adversarial examples, and then we'll talk about how they can be applied to different components of the self-driving stack. Let's start with some background. Computer vision has improved dramatically in the past decade thanks to neural networks. Today, image classifiers can even outperform humans on image recognition. However, these neural nets are infamously vulnerable to adversarial examples. Adding a small and imperceivable amount of noise onto an input can cause the neural network to fail, even though the perturbation doesn't affect human judgment. While adversarial examples were first introduced for image classification, they've been extended to many other applications, including semantic segmentation, object detection, and natural language processing. How are adversarial examples generated? The main idea is to perturb the clean input minimally while changing the model output. In a white box setting where the model is known and differentiable, we can generate perturbations with gradient-based optimization. Similar to optimizing the weights of a neural network, except now we're fixing the weights and optimizing the input instead. In more challenging but practical settings, the model will be unknown or not differentiable. In this case, the attacker can still use black box optimization methods that rely on querying the model. Even when queries are not available, weaker transfer attacks can still be achieved by training a surrogate model to estimate the gradients of the victim model. When it comes to how we want to modify the output, there are two broad categories: targeted and untargeted attacks. Targeted attacks try to induce a specific target output. For example, changing the label from banana to snail. Untargeted attacks do not specify a target output. Anything is fine as long as it's not the correct output. For example, in this case, it would be changing the label to anything but banana. We've seen perturbations against a specific input. However, if the input changes slightly, for example, due to an object moving, the perturbation might not be effective anymore. This makes it difficult to launch attacks in the real world where objects are usually in motion. Towards more robust attacks in the real world, we can train universal adversaries by training a single perturbation against the entire training set and minimizing the expected accuracy. The result is a perturbation that is input agnostic and can be used to attack any input. Furthermore, this will mean that during the attack, we can just use the trained adversary without incurring any computation costs. Finally, because we can attack any input, we do not need prior knowledge of the scene to execute an attack. To be threatening in the real world, The adversarial examples also need to be physically realizable. In this work, the authors show an adversarial sticker which anyone can print out and stick onto an existing image to fool classifiers. The sticker is universal in that it's adversarial when placed on any location, with any orientation, and on any image. Here's another example of a physically realizable attack. The authors 3D print a mesh of a turtle, but pictures of the turtle are falsely classified as a rifle or something else. This object is universal in that it can fool classifiers when seen from any viewpoint. We've seen that practical real-world adversarial attacks against neural networks are possible. On the other hand, self-driving vehicles rely heavily on neural networks, and self-driving vehicle is a highly safety-critical application. Therefore, it's important that we study adversarial robustness in the context of self-driving. Moving on to adversarial attacks in self-driving, let's start with perception. 3D object detection is the first part of the autonomy stack, and successfully disrupting perception can be detrimental, as perception failures will propagate to downstream tasks. What are we looking for when we design these attacks? First, the adversary has to be physically realizable to be a real-world threat. Second, the adversary should be robust to motion, as everything is moving relative to the ego vehicle. Third, the adversary should hide objects, as colliding onto unseen objects is the most dangerous outcome. And finally, the attack should not require too much computation during execution. Now let's look at existing adversarial attacks against modern 3D object detectors. We'll focus on point cloud inputs, as LiDAR sensors are the most popular sensing hardware in self-driving perception. Adversarial attacks on point clouds are slightly different from images, as one can move points, add points, and remove points, whereas in images, we can only modify pixels. However, arbitrary modifications to points are often not physically realizable, as point clouds are often generated by sensors with fixed angular frequencies. Therefore, some works try to modify points as if there was an underlying surface to make the attack more physically realizable. But how do we actually modify the point cloud readings from sensors? Some works have used a spoofing device to send the LiDAR sensor false signals and create adversarial points. This can cause perception to hallucinate false positives. In an extension of this work, the authors launch efficient black box attacks by collecting false positive examples from existing datasets or simulations. Here, they focus on occluded or faraway objects, as they have less points and therefore make a smaller perturbation to the scene. Then during attack, instead of performing optimization, the attacker can directly place these examples into the scene. Spoofing devices, however, may be difficult to execute in practice as the LiDAR sensor moves. A more reliable way to generate adversarial point clouds is to place an adversarial object into the scene. In this work, a physically realizable adversarial mesh generates a point cloud which creates false positives. Previous works mostly focused on false positives. However, false negatives and colliding onto unseen objects may be much more dangerous. So, in our work, we present a method to hide other vehicles on the road. To make the attack physically realizable, we parameterize the adversary as a 3D printable mesh. The mesh is placed on vehicle rooftops for several reasons. Easier to place due to gravity, less prone to occlusion, and it resembles realistic rooftop cargos like furniture and sports equipment that we might see in the real world. Finally, we aim to make the adversary universal, hiding vehicles across time and space with high confidence and making the adversary robust to other variations in the environment. By placing our adversarial mesh on a vehicle roof, we can hide the vehicle with high probability no matter what kind of car it is, what the pose is, and what the environment is. Note that our mesh is the same for all the vehicles. As shown in the illustration, the same adversarial mesh successfully hides 4 different vehicles at different positions in different scenes. Furthermore, with a single universal adversary for all inputs, no optimization is required during the attack. Therefore, we train to discover a single mesh that is an adversary against all vehicles in the training set. This makes the adversary input agnostic under the training distribution. Towards this goal, we use a differentiable renderer to bridge the gap between the mesh representing the physical object and what the sensors see, which is a point cloud. And then we optimize an adversarial objective targeted at minimizing detection scores to hide vehicles. In particular, to minimize detection scores, our adversarial loss minimizes the confidence of all bounding box proposals. In addition, we weigh the proposals by their intersection over union with the ground truth bounding box to prioritize high-quality proposals. We mainly rely on black box optimization as it's applicable to all models, whereas some detection models are not differentiable end-to-end. Even when gradients are available, we find that white box attacks are of similar strength since black box optimization works well for low-dimensional mesh parameterization. Let's see an illustration of how our algorithm works. First, we start with a lidar sweep, which is the input to our detectors. Then we aim to hide a vehicle from the detector. Here, the vehicle is highlighted in green. To do this, we add a physically realizable object into the scene. Here, we choose a mesh as our representation, as it can be 3D printed. Then, we use a differentiable renderer to render the mesh into a point cloud and attach it to the top of the vehicle. To determine the location of the roof, we fit a vehicle mesh to the point cloud. We then add the mesh points onto the vehicle rooftop to create the modified scene. The modified scene is then processed by a detector to produce output bounding boxes. To optimize our adversary, we apply the adversarial loss targeted at hiding the vehicle. Here is a qualitative demonstration of our attack. On the left is a 3D view of the scene, the vehicle, and the rendered adversary. The same adversarial mesh is used throughout the entire video. Notice in the top right, in the original snippet, the target vehicle is consistently detected. However, on the bottom right, after adding the adversary, the vehicle is hidden in most frames. We evaluate our attack against models with different input representations. We use Pixar, which takes occupancy voxels, and a variation taking density voxels. Point RCNN, which processes raw point sets, and point pillars, which divides points into pillars and extracts features in each pillar with a point net. We evaluate the attack on Kitty. Our metric is attack success rate, which is the percentage of originally detected vehicles that are not detected after perturbation. We also include transfer attacks, where we train the mesh to attack one detector and evaluate it against another detector. In this table, rows describe the models used in training, and columns are models during evaluation. Therefore, the diagonals represent standard attacks. Our results show that different input representations have different levels of vulnerability. Here, off diagonals are transfer attacks. We observe a high degree of transferability between models with the same architecture, as is the case in the two Pixar variants. We observe low transferability elsewhere, indicating input representations may have a large effect on the features a model learns, as well as its vulnerabilities. To verify that input representations do impact robustness, we conduct an experiment where we replace Pixar's occupancy voxel representation with pillar feature encodings. Here, we're able to use the same backbone and training schemes since both Pixar and point pillars perform 2D convolution in bird's eye view. Here, Pixar Star is significantly more robust purely due to different input representation. This suggests that additional point level reasoning before aggregation in the height dimension increases robustness to rooftop objects. Then we compare white box against black box optimization and find that black box optimization is not much weaker. Furthermore, we benchmark against the mesh that is used for initialization of our adversarial attack. Although the initial mesh is similar in size, it has little impact on detection recall. On the other hand, the adversarial mesh drops recall significantly, showing that geometry is indeed adversarial. Even without malicious intent, These scenarios can coincidentally occur in practice in the form of rooftop cargo. So we conduct experiments where we initialize the mesh from common rooftop objects and additionally place an epsilon constraint on mesh vertices to maintain resemblance to the original. We measure attack success rate again and find adversaries that are very similar to real-world furniture and sports equipment. Particularly, we find larger objects like couches and canoes to be especially effective. Smaller and thinner objects like chairs and bikes are weaker as they generate less lighter points. Finally, we conduct a pilot study on defense with two approaches. First, we perform data augmentation by adding random meshes to vehicle rooftops during training. By training against random rooftop objects, we can greatly improve robustness. Next, we use adversarial training, which adds adversarial meshes into the scene during training. Here, we simultaneously update the adversarial mesh and the model. And furthermore, we show detection performance on the unperturbed dataset in the rightmost column and show that a defended model achieves similar or better performance. Therefore, by training against their adversaries, models become much more robust to out-of-distribution rooftop adversaries. In addition to LiDAR sensors, which are commonly used for their ability to capture rich 3D geometry, other sensory inputs can complement LiDAR to improve perception. One common example in self-driving is the use of cameras, which capture images with rich appearance. However, images have been found to be very vulnerable to adversarial attacks when processed in isolation. Therefore, it's important to consider how the inclusion of images affects the robustness of multimodal perception systems. There are existing works which paint vehicles to create adversarial textures, and as a result, these vehicles are camouflaged and hidden from image detectors. However, this attack does not target multimodal detectors. In another work, the authors perturb both image and LiDAR to study how image features affect robustness and find that image perturbations are much more effective than LiDAR. However, the attack perturbs image and LiDAR independently, which may result in perturbations that are. In this work, the authors perturb both image and LiDAR to study how image features affect robustness and find that image perturbations are much more effective than LiDAR. However, the attack perturbs image and LiDAR independently, which may result in perturbations that are inconsistent across the two modalities. To hide vehicles in a realistic manner, we extend the previous rooftop cargo attack to include a textured mesh. Rendering the same object into the two modalities ensures that perturbations are physically realizable. We start by extending the LiDAR simulation pipeline to accommodate images as well. Here we have a LiDAR sweep and an image input. The host vehicle is again highlighted in green in the LiDAR and clearly visible in the image. Again, we perform mesh fitting to approximate the pose of the host vehicle, which determines the pose for the adversary. To handle occlusion in images, we also need to know the depth of each individual pixel, which is not available in the raw capture. Here, we use a depth completion model, which takes the image of interest and sparse ground truth depth from the LiDAR scan to obtain a dense estimate of each pixel's depth. Then, we render the adversary and place it into the scene and discard occluded pixels or LiDAR points by simply removing points or pixels with greater depth along the same ray. Finally, we apply a simple directional lighting model to approximate sunlight and enhance the realism of our simulation. Then we extend the previous work by incorporating the image simulation module and replacing the LiDAR-only model with a model that processes both image and LiDAR. To fuse image and LiDAR features, the 2D image features are projected into 3D. In addition, we introduce a false positive component into the loss function. The false positive loss encourages high confidences in all proposals which do not overlap with any ground truth bounding box. We perform the attack on two datasets, Kitty and an internal dataset, Zenith. We evaluate the success rates of false negatives and positives separately in our metrics. To attack a single modality, we disable gradient flow to the other untargeted modality during the backward pass. Our experiments are all conducted on the MMF model. And note that while we only focus on a single model, our method is general and works for any differentiable model. We perform attacks on a LiDAR-only detector and a detector which uses both LiDAR and images. Overall, we find that multimodal models are slightly more vulnerable to the LiDAR-only counterpart. For the multimodal model, we also experiment with 3 attack settings: attacking LiDAR only, attacking image only, and attacking both. In addition, we consider a baseline of a mesh with randomly generated geometry and texture. We find that successful attacks on image LiDAR models are mostly caused by brittle image features. Note that perturbing LiDAR alone is not very effective, and on the other hand, perturbing images alone is almost as effective as perturbing both. We also conduct black box transfer attacks between the 2 different datasets, which are captured with different sensor hardware configurations, like image resolution and LiDAR calibration. Furthermore, these datasets are also captured at different geographic locations. Still, we observe a small degree of transferability between the 2 datasets, as the attack success rate after transfer is still much higher than using a random mesh. Here is a demonstration of the attack on Kitty. While both LiDAR and image are perturbed, we only show the image here as it's easier to see the host vehicle. Notice the flickering of the detections after perturbation on the top. In contrast, the unperturbed vehicle on the bottom is consistently detected in every frame. Now we show some qualitative examples of false positives. We mostly observe them in distant locations far away from the host vehicle. We show these false positives in bird's eye view LiDAR sweeps since they're too small to see in the image. Upon visualizing the image features after perturbation, we can see the adversary induces strong adversarial features in the image space. These strong features are then projected into 3D, and after projection, they dominate the 3D LiDAR features after fusion and create false positives. Finally, we explore several defense methods against our attack. First, we employ JPEG compression and decompression on the image inputs and find that it has little effect. Next, we again find adversarial training to be very effective. And furthermore, by combining feature denoising with adversarial training, we can achieve a very strong defense against false negatives. But the effect on false positives is much weaker. We suspect that this is because false positives are also caused by inaccurate associations between 2D pixels and 3D LiDAR points during fusion. And such inaccuracies cannot be corrected through adversarial defenses. Now let's talk about adversarial attacks against communication. We've studied adversarial robustness at the sensor input level, but how about during vehicle-to-vehicle communication? First, we'll give a refresher on V2V. We start with each vehicle collecting sensory inputs. These sensory inputs are then processed into feature maps and compressed, and then transmitted as messages. The receiver then receives these vehicles and decompresses them. The messages are then aggregated by a graph neural network. And finally, aggregated messages are finally processed to generate detection outputs. As we've seen in the V2V section of this tutorial, V2V communication can boost perception performance drastically. However, what happens if an attacker can tamper with the messages? Then communication channels can be compromised to inject adversarial messages. While existing security protocols can provide adequate security for communication, additional levels of redundancy are always welcome, especially in safety-critical applications like self-driving. Therefore, we study adversarial attacks to improve robustness of communication systems at the neural network level. We find that adversarial messages can severely degrade performance. Also, by setting a small epsilon constraint on the perturbations, the adversarial messages are almost indistinguishable from the original, making them difficult to detect as well. Now we'll discuss how to create these perturbations that are added on top of messages which are intermediate network representations. Again, our goal is to attack object detection, where detectors output proposals composed of a bounding box, class, and confidence score. Here, an adversarial message is crafted to attack all detections in the same scene instead of just for a host vehicle. We can attack the output by changing the class label of these proposals. We can create false negatives by changing classes of detected objects to background class to make the objects disappear. On the other hand, false positives can be generated by changing background classes to an object class to make the detection model hallucinate. In a white box setting, attackers can apply this adversarial loss to create adversarial messages using gradient-based updates and generate false class labels. However, full access to the model running in the SDB is not practical. In a scenario where communication channels are compromised, transfer attacks can still be executed. Here, the attacker has write and read access to the communication channels, but does not have any access to sensory information from the vehicles. To perform a transfer attack, the attacker needs to train a surrogate model to approximate the gradients of the target model. By doing so, perturbations generated by the surrogate model will transfer to the intermediate features of the target model. However, this requires that the surrogate produces similar intermediate features as the target model. While the attacker cannot access the target model, the intermediate features of the target model are available by spying on the communication channel, as we've assumed previously. Therefore, when training a surrogate model, we use a discriminator to match the distribution of the surrogate's intermediate features to those of the target model. We use a discriminator instead of distillation since the communication channel does not contain sensory inputs. Therefore, we do not have paired data of the sensory input and the associated intermediate feature. In addition, the surrogate model is also trained to perform the same perception task to imitate the behavior of the target model. Once the surrogate model is trained, we can execute attacks by using gradient-based updates to generate a transferable perturbation using the surrogate model, and then add it to the benign message. In contrast to a universal attack that we've shown previously, where computation is not required during the attack, here we need to perform optimization at every time step in an online manner, which can be too expensive. Luckily, in an online setting, we can exploit the redundancy between consecutive frames to create more efficient attacks. In self-driving, consecutive frames are often collected milliseconds apart and will be very similar to each other. Specifically, we can use the perturbation from a previous frame as initialization for the next frame. In addition, we apply a rigid transformation at every time step to account for ego motion. By doing so, we can synchronize the perturbations with the movement of sensory measurements relative to the ego car. Here are some results. We plot the average precision at different numbers of agents. We show a no attack baseline and a noise baseline where random uniform noise with the same epsilon bound is added. We can see that the random noise has little effect on performance. Our white box attack is able to drop average precision significantly at few agents, but the model becomes more robust with more agents. Our transfer attack is able to achieve a small degree of success, but as expected, is much weaker than a white box attack. Here is a qualitative example. We show the benign feature map on the top left and the perturbation on the top right. The perturbation is very small, as can be seen from the color scale. On the bottom left, the unperturbed message produces mostly correct detections. After adding the perturbation, we can see all the false positives and false negatives on the bottom right. Here, we demonstrate the necessity of using domain adaptation to align the intermediate representations of the surrogate model. We compare generating perturbations with three models: the original model, a surrogate trained without domain adaptation, and a surrogate trained with domain adaptation. We evaluate in a setting with only two SDBs in the network. First, Note that using the original model to generate perturbations is equivalent to a white box attack and is very strong. Then notice that the attack is completely ineffective without domain adaptation. Next, we evaluate cross-inference, which is using the surrogate model to process the intermediate features of the target model. This evaluates how well the surrogate model imitates the target model. And we can see that domain adaptation makes a huge difference here once again. Here is a qualitative demonstration of domain adaptation. We show 4 channels of the intermediate feature maps. Notice the similarity between the target model and the surrogate model with domain adaptation in the first and third rows. But without domain adaptation in the second row, the features look very different. Finally, we conduct an ablation on our methods to perform efficient online attacks. In the no warping baseline, we do not perform rigid transformations to account for ego motion, which results in a slightly weaker attack. In the independent setting, we completely ignore temporal redundancy and treat each frame as an independent sample. Therefore, we do not reuse previous perturbations, and the attack becomes significantly weaker here.
Hi everyone, I'm Jin Kang. Previously, we showed how to build robust autonomy systems on perception and communication. We now turn our attention to study how to generate scenarios that might cause failures for the full autonomy stack. Robust perceptions are not the end, since there are also some adversarial behaviors that might cause the failures of autonomy systems. As self-driving vehicles perform better in natural and well-behaved scenarios, simulating those behaviors becomes more important for the safety test. However, identifying those scenarios is challenging, as there are exponentially many of them due to the combination of possible lane topologies, actor configurations, and velocity profiles. Conventional practice in industry for comprehensive testing is the semi-autonomic process that relies on the human expertise to create an initial scenario set, where each scenario contains at most 1 or 2 actors of interest with specific initial locations and trajectories. Scenario variations are then programmatically created by varying the actors' locations and the velocity profiles. While such scenarios are valuable, they only evaluate simple interactions with the SDV and do not test complex multi-actor interactions, such as lane merging and unprotected left turns in dense traffic scenes. Moreover, human involvement makes this process time-consuming and difficult to scale. Manual design may also result in missing testing configurations that identify unexpected failure modes. To address this problem, recent works aim to automate the generation procedure by searching over the set of possible scenarios and identifying high-risk ones according to a specific cost function. Note that we also want the scenario to be physically plausible. If an adversarial actor is chasing the SDV and trying to hit it directly, then there is nothing we can do. The right figure shows a reasonable high-cost scenario which is desired for the simulation and testing. For simplicity, most previous works only consider a motion planning module that have access to the ground truth state of the actor in the scene. In this way, they only need to focus on modeling dangerous actor behaviors. Moreover, it's fast to generate and evaluate scenarios since the perception systems are omitted. However, this overlooks the fact that many adversarial scenarios often involve actors that are hard to identify due to the occlusion, or they have trajectory plans that can be difficult to localize and forecast. Such issues in the perception and motion forecasting modules can generate compounding errors that ultimately cause planning failures. To mitigate this issue, some other works test end-to-end image-based self-driving systems. However, the adversarial scenarios they generate are either generated at a very small scale or with respect to simplified imitation learning modules that do not reflect the autonomy systems for modern self-driving vehicles. Additionally, they usually modify high-level actor behaviors or create physically unreliable trajectories, which lacks the fine-grained controls in modeling actor behavior. Therefore, we need a scalable approach to identify physically plausible challenging scenarios, starting from the sensor data for the modern autonomy systems. Starting from LiDAR data matters since it allows us to conduct end-to-end testing and training with those simulated scenarios. This table provides a summary of recent works. Most prior works generate scenarios only for a handful of scene configurations and are adversarial only with respect to the planning module. We propose a scalable approach to modify existing traffic scenarios to cause the full autonomy system failures. Our approach tests modern autonomy systems and generates over 4,000 unique adversarial scenarios. We frame the generation of worst-case scenarios as the black box adversarial attack. Adversarial works as follows. Given an existing scenario and its original sensor data, we first perturb the actor's trajectories in a physically plausible manner. Next, we update the sensor data to take the actor perturbation into account. We then evaluate the autonomy systems on the modified scenario, compute an adversarial objective, and update the proposed perturbation using a black box search algorithm. Adversarial works for any LiDAR-based autonomy stack. Adversarial's objective is to increase the risk for the autonomy system's planned tall star. Our adversarial objective consists of 3 parts. An imitation learning loss represents the deviation from the expert's trajectory. A safety cause to encourage a collision with other actors. And traffic rule conflict cause that encourage the autonomy plan to have lane violations and to be dangerous. To ensure the realism of simulated behaviors, we parameterize the actor behavior with a bicycle model and set the physical constraints such as staying on the road and not colliding with other actors. Given the perturbation on the actor motions, we conduct realistic LiDAR simulation to accurately reflect the updated scenes. The modified LiDAR history is the new input to the autonomy system. The LiDAR video shows that the generated scenarios are realistic and match the desired perturbation. We now show the adversarial generated scenarios for the P3 autonomy system. We focus on an open loop scenario evaluation setting in which the evaluated autonomy systems take the past 1 second LiDAR data as input and output a 5-second trajectory plan. We then unroll this 5-second plan and the other actor trajectories for 5 seconds and evaluate the autonomy system performance during that time horizon. The SDV is in blue and the perturbed actor is highlighted in red.
This scenario has a stationary bus in front and a crossing pedestrian. In the 5-second trajectory output from the P3 system, the SDV only moves forward a little. Adversarial perturbs the initial states of the bus in red by moving it into the left lane. Now, the P3 autonomy system does not detect the pedestrian, and the SDV's 5-second plan collides with it. To understand why the SDV behaves as it does, we now show the forecasted occupancy visualizations of the P3 autonomy system. The occupancy for pedestrians is shown in light green. As we can see, the pedestrian is perceived as part of the bus's occupancy area, and hence the system misses the pedestrian detection. Here's another example. Originally, the blue SDV lane changes smoothly to avoid the stationary bus in front. Adversarial perturbs the bus to instead be reversing and blocking the road. Now, when the SDV attempts to lane change, it is rear-ended by a high-speed vehicle from behind. From the occupancy visualization, we can see the predicted bus occupancy blocks the whole lane. This causes the SDV to predict a dangerous large turn to avoid the bus, but does not properly account for traffic from behind.
Adversarial generates challenging scenarios for a wide range of state-of-the-art autonomy systems. As we can see, they initially achieve a relatively low collision rate on natural real-world scenarios. But with adversarial, we increase the collision rate by over 200% compared to the original set. These challenging and physically plausible scenarios provide insights into how different autonomy systems compare and how they fail. Adversarial scenarios can also be used in autonomy system training to improve the performance. We take 2 pre-trained SOTA autonomy systems, PLT and P3, and fine-tune them on a dataset augmented with adversarial scenarios. Robust training with adversarial generated scenarios helps improve the performance on both the original and adversarial scenarios, making the autonomy system safer. In conclusion, We touched upon how to generate adversarials to identify vulnerabilities in the context of perception, vehicle-to-vehicle communication, and the full autonomy system. We then show how we can use these adversarials to improve the robustness of the current self-driving system. Thanks for watching.
Okay, thanks, guys. If anyone has any questions, feel free to ask.
Yeah, also there is another break after this session.
Yep. And the next session after this is building HD maps, which will be at 4:55.
Mhm. Cool. I think we can go to the next session, building the HD maps.
Hi, everyone. My name is Justin. I'm a research scientist at Wabi. In this tutorial, we will cover HD maps for autonomous driving. Two types of maps are used in self-driving cars: topological maps, as well as high-definition maps, typically referred to as HD maps. In this talk, we will provide an overview on what these maps are, why they are useful for self-driving, as well as how to create them. We will cover what we can do when the underlying map has changed or is missing. Furthermore, we will also talk about how to perform cooperative multi-agent mapping. In the first section, we will go over sparse topological maps. Topological maps contain a diverse set of attributes, such as road topology, the number of lanes in a street segment, the location and shape of buildings, or the direction of travel. These topological maps are used by self-driving teams to have an understanding of the potential difficulty of a given geographical area. They are also used online by the self-driving vehicle to help plan a high-level route to go from point A to point B. There are many data sources that can be exploited to generate topological maps. Cameras mounted on windshields are available at scale, as many drivers use them for insurance purposes. Aerial images captured by drones, planes, and satellites can also be used. And of course, we can also use self-driving vehicles. In the literature, obtaining topological road graphs can be divided into three different approaches: segmentation-based, followed by heuristics, energy-based, and neural network-based. For the first category of segmentation-based methods, many works apply road binary segmentation on aerial or satellite imagery, followed by post-processing algorithms to obtain the road network. The strength of these methods lies in that one can use state-of-the-art segmentation methods to obtain the roads. However, this could also be a weakness, since the road network extraction depends on the segmentation quality. For example, if there are occlusions due to building shadows and trees, the extraction might fail. One is also dependent on the post-processing algorithm used, which might prove brittle. Along this direction, for example, Matthews et al. Apply a thinning algorithm to the segmentation to obtain the road topology. However, there might be missing road segments in the graph where the segmentation fails. To alleviate this issue, they apply A-star search to connect the disconnected segments. Rather than using segmentation followed by heuristics to obtain the road network, some works use a more principled approach by formulating the problem of road topology extraction as an energy optimization task. This way, one can encode and optimize in a structured manner the semantic and geometric priors found in the task. For example, Matthews et al. Enhance OpenStreetMap's road center lines with road width by doing inference in an MRF. In their energy terms, they use cues such as road segmentations and image edges obtained from aerial imagery. They also incorporate geometric priors, such as the smoothness of the road boundaries. While mathematically more structured, these methods rely on handcrafted features and fail to produce the fidelity and precision
required for autonomous driving. As previously seen, segmentation and energy-based methods typically employ many handcrafted features in their design and are not high fidelity. A learning-based neural network approach for obtaining the road topology structure can help alleviate these issues. Thus, in more recent works, methods have used recurrent neural networks to iteratively draw the road topology graph. For example, in Li et al., they use an RNN-based approach and iteratively predict the vertices of road polylines. Similarly, they also predict in the same model polygons for building contours. However, one challenge with these methods is the difficulty in training these RNNs to predict these structured outputs. Finally, the neural turtle graphics work of Chu et al. Goes one step further than simple topology extraction and actually generate new roadmaps. In particular, the roadmap is considered as a spatial graph, and by using RNNs, they sequentially generate nodes of the graph conditioned on the already generated graph to obtain a road network. The model can also be conditioned on a set of attributes to control the style of the generated road network, as one can see in the figure on the right, where maps similar to New York and London have been generated. And here we see a video of the results of this work. We see that conditioned on city labels, the method generates layouts very similar in style to the actual cities. Next, Joyce will talk about HD maps.
Thanks, Justin, and hello everyone. My name is Joyce Yang. I'm currently a researcher at Wabi as well as a PhD student at the University of Toronto. Today, I'll be talking about high-definition maps. In addition to the sparse topological maps you just saw, the second type of maps used in self-driving vehicles are high-definition maps, which contain both detailed geometry and semantic information about the environment. High-definition maps are used for precise localization of the self-driving vehicle, and they can also be used as prior knowledge for the autonomy system and for simulation as well. Self-driving companies are interested in creating globally consistent and high-definition 3D maps of the world. In the industry, many passes over the same area are typically required for these maps to be complete. However, we would like to reduce this requirement as this is very expensive. Furthermore, maps typically require large amounts of memory to store, preventing them from being able to be produced and used at scale, and we would like to address this limitation as well. Finally, we would like the maps to only contain permanent elements that we will see every time we drive around the mapped area. So how do we build these HD maps? Building HD maps is typically a four-step process. In the first step, we select the operational domain we would like to build the maps for. Next, we drive around these selected areas and collect raw sensor data with a fleet of vehicles. Then we process the raw data and build the geometric maps that contain the 3D geometry information. Finally, we conduct labeling to add semantics in our HD maps. We'll first talk about geometric HD maps. With the collected raw data, we build the geometric HD maps in 3 steps. We first split the raw data into small chunks and fit trajectories for individual chunks. This process can be performed in parallel. We then align all trajectories in a massive global optimization problem, which can be solved with graph SLAM techniques. Finally, we assemble the chunks to build a globally consistent geometric map. We next explain SLAM, which stands for simultaneous localization and mapping. SLAM is an important technology to jointly estimate both the trajectory and the 3D map. SLAM systems typically consist of a front end and a back end. The front end takes the raw sensor data as input and performs feature extraction to parse the raw input into intermediate representations. Data association is then performed on the intermediate representations to align consecutive frames as the vehicle travels. In addition, the frontend is also in charge of loop detection when the vehicle is revisiting the same area. The SLAM frontend then passes the process sensor observations to the backend, and the SLAM backend then performs graph optimization to estimate and refine both the vehicle poses and the 3D map. We'll first discuss the SLAM frontend. The SLAM frontend parses and associates raw sensor data to derive constraints between the 3D map and the vehicle poses. The specific implementation of the frontend is sensor dependent. Common sensors in a SLAM system include LiDAR, cameras, inertial measurement units IMU, GPS, and wheel encoders. In the self-driving industry, it is common to use all these sensor types to build HD maps. We next briefly discuss LiDAR-based frontend and camera-based frontend. In a LiDAR-based SLAM system, the frontend typically performs 3D registration between LiDAR scans for tracking and loop closing. The 3D registration can be performed with classical methods such as ICP and its variants, and there are learning-based approaches as well. On the other hand, camera-based SLAM frontend processes camera images as input to perform pose estimation during tracking and loop detection. Camera-based frontend can be generally divided into direct and indirect methods. Direct methods such as DTAM, LSD SLAM, and DSO use the raw image pixel intensities directly and optimize with photometric error in the backend. On the contrary, indirect visual SLAM systems such as monoslam, PTAM, and warp SLAM represent images as sets of key points with classic feature extractors. Image association is then performed by finding key point correspondences, which are optimized with geometric error in the backend. Generally speaking, direct methods usually use all pixels to leverage all information of an image, which can lead to dense maps and large, expensive, and challenging optimizations that oftentimes require good initializations to converge to optimal solutions. However, it is worth pointing out that there exist direct methods, such as DSO, that use sparse pixels to reduce computational costs. On the other hand, indirect methods typically use sparse key points, which are more computationally efficient. However, the sparse key points do not leverage all information from an image, which might result in inaccurate estimates. Next, we will discuss the SLAM backend. With the raw sensor data, the SLAM frontend constructs a factor graph where the nodes are the parameters associated with the 3D map and the vehicle poses, and the edges are the constraints obtained from the sensor observations. The SLAM backend then takes this factor graph as input and performs graph optimization to jointly refine the 3D map and the vehicle poses. The backend graph optimization can be divided into two approaches. The classic filtering-based approach uses an extended Kalman filter, which will be covered in the localization tutorial session. The vanilla EKF typically marginalizes all vehicle states other than the current state and results in a compact graph, but it suffers from inefficient graph updates as well as inconsistencies from linearization errors. On the other hand, modern smoothing-based backends jointly optimize poses and geometry with nonlinear least square errors, but optimization over the entire graph can be computationally expensive. To improve computational efficiency, smoothing-based backend typically selects a subset of all frames as keyframes and only performs optimization over them instead. In addition, sliding windows are typically adopted to optimize poses and geometry only over a window of most recent frames. Compared with filtering-based approaches, it was shown that in monocular visual SLAM systems, smoothing is more efficient if high accuracy is required. There are generally two approaches to integrate learning into a SLAM system. Recent end-to-end visual SLAM systems mostly focus on direct methods and use neural networks to jointly learn depth and poses with the photometric loss. Alternatively, several approaches only learn parts of a SLAM system. For example, recent works have successfully learned the loop closing module of a LiDAR SLAM system, the 2D front-end features in a visual SLAM system, and the keyframe selection stage of a visual SLAM system. We might also need to handle asynchronous sensors for a SLAM system. Self-driving cars are usually equipped with multiple cameras to make more observations of the surrounding environment. Existing multi-view SLAM systems all assume that the multiple cameras fire at the same time. However, in practice, the multiple cameras can be asynchronous due to technical limitations or by design. For example, the cameras can be synchronized to another sensor, such as a spinning LiDAR, which is a common setup in recent self-driving datasets. To tackle this problem, asynchronous multi-view SLAM formulates a general SLAM framework that accounts for multiple asynchronous cameras. The results show that using multiple cameras and correctly accounting for their asynchronous nature is important towards accurate and robust SLAM in challenging real-world environments. We next show a video of AMV SLAM in the real world. On the top left, we only show the view from the front middle camera, while in practice, the system takes input images from all 7 cameras. We show the estimated continuous time vehicle trajectory in green and the generated map points in black. The AMV SLAM system successfully estimates its trajectory through the busy streets and manages to close the loop correctly. While the previous example shows maps generated with a multi-camera SLAM system, in practice, we use more sensors. The result is high-fidelity maps of our cities. In the video, you can see reconstructions using both LiDAR as well as cameras. In addition, we would like to remove potentially dynamic objects such as moving and parked cars. We do this by exploiting state-of-the-art semantic segmentations. This is illustrated in the video. Filtering these dynamic objects is important and results in much crisper maps. This is illustrated in green versus red. Next, Justin will talk about generating the semantic elements of the map.
On top of geometry, HD maps contain rich semantic information, such as the precise location of lane and road boundaries, crosswalks, and intersections. Furthermore, they encode the traffic regulations. For example, lane conflicts, traffic light to lane associations, and information traffic laws described in signs. The semantic HD map should have several desirable properties. First, we would like to have highly accurate semantic labels. Moreover, they should be scalable to scenes in the real world. However, there are several challenges. First, the maps change all the time due to construction or urban planning changes, especially during a pandemic. In addition, the typical map build process in many companies involves a fleet of vehicles passing multiple times across the same area to build accurate geometric representations of the world. As a result, annotators have to label the location and attributes of all the semantic elements, which can be expensive and labor-intensive. These mentioned challenges are some of the main obstacles in deploying autonomous vehicles at scale. As such, we need to automate semantic map building to scale self-driving. And also don't forget that we are interested in building large-scale maps of our neighborhood, cities, countries, and beyond. In order to create semantic HD maps at scale, we need to design approaches that can leverage both machines as well as humans. Humans are necessary as the level of fidelity required in self-driving is way beyond what the state-of-the-art is. Self-driving companies are particularly interested in designing approaches where machines and humans can collaborate to minimize the total dollars spent. Knowing where the road boundaries are, that is, delineating the separation of the drivable surface of the road from sidewalks, is crucial for safety and navigation. Currently in the industry, human annotators draw these road boundaries from scratch as part of the HD map production. This is a very expensive task since we need to annotate whole cities, and as such is not scalable. As part of the annotation process, first, one typically aggregates LiDAR and camera images from multiple passes of the mapping vehicles through an area to create BEV images of a certain resolution, for example, 5 centimeters per pixel of the scene. Next, hundreds of human annotators look at these BEV LiDAR and ground camera imagery and draw out the road boundaries one by one as polylines. There are also multiple QA rounds to make sure that these polylines are correct and precise. The question is, can we automate this process so that human labelers only need to do the QA and adjust the wrong predictions or draw the missed boundaries rather than annotating everything from scratch? Hence, we tackle this problem by directly outputting polylines for each road boundary from BEV inputs. The input to the model is the LiDAR and BEV imagery and LiDAR elevation gradient, which are fed to a deep convolutional network that outputs 3 feature maps. Firstly, an inverse distance transform image that encodes the relative distance from each pixel in the image to the closest road boundary pixel. Secondly, an endpoint heat map, which is the probability that a pixel is the endpoint of a road boundary. And finally, the road boundary direction map, which encodes the normal direction towards the closest boundary. Finally, these 3 feature maps are fed into a convolutional RNN, which iteratively attends to rotated regions of interest in the image and outputs the vertices of a polyline corresponding to a road boundary. In this video, we see the results of our model on the test set. On the left in the red is the ground truth road boundary polylines. On the right, we see the outputs of our model. The yellow rotated boxes correspond to the region of interest that the recurrent CNN attends to sequentially. The blue dots are the predicted vertices. Note that at intersections and areas of high curvature, the model has learned to place the vertices close to each other. We are interested further in estimating the crosswalks. Existing approaches focus on predicting the existence of a crosswalk, but do not provide an accurate localization. Instead, crosswalks are typically crowdsourced and manually drawn. In our approach, we want to leverage the road boundaries we had before to obtain accurate crosswalk polygons. To do this, we feed LiDAR and BEV imagery into a CNN to output inverse distance transform, segmentation, and angle heat maps. Next, using the road boundaries as a coarse map to define the crosswalk boundaries, we exploit structure prediction to create the final drawing. By leveraging distance transforms and integral accumulators, efficient exact inference is possible. Our model achieves 96.6% automation of all crosswalks. In this video, we showcase our model results in the top right, compared to the ground truth in the bottom right. We see that our model draws very accurate crosswalks when compared to the ground truth. Previously, we have shown how to predict accurate road boundaries and crosswalks. Now, we want to estimate even more fine-grained map elements. We want to estimate lane boundaries. Lane boundaries have to be very precise to prevent the SDV from inadvertently crossing into other lanes. In particular, we focus on highways, which offer interesting topologies and are the first step before automating this task for cities. Instead of requiring multiple passes of a vehicle, which is costly, here we aim to map from only one pass of the vehicle through the area. We formulate the problem as a discovery and inference in a directed acyclic graphical model, that is, a DAG, where the nodes correspond to geometric and topological attributes. Given a temporally aggregated LiDAR point cloud projected into BEV, we aim to find the maximum a posteriori of the probability over all the possible DAGs that could describe the road. The probability distribution of each DAG can be factorized as the product of the probability distribution of its vertices. Each vertex conditioned on its parent is a random variable with the following three attributes: the direction of this vertex given the parent vertex, the geometrical position of the vertex, the topological state of the vertex, as in no change, fork, merge, and stop drawing. The space of all possible graphs is exponentially large, so we greedily construct the graph and compute the geometric and topological properties of each vertex. We demonstrate the inference process with the figures on the right. On the top, assume we have the already inferred DAG at the current time step. Next, we find the direction of the next vertex highlighted in the yellow rotated region of interest. Then we infer the position of the vertex in the region of interest and its state, which is inferred to be a fork. At this fork, we continue drawing the current lane boundary as is, but emanate a new one corresponding to the new lane boundary at the fork. Of course, we want to leverage the power of neural networks so that we use neural networks to estimate these probabilities. These probability distributions are complicated. As such, we use neural networks to approximate them and iteratively draw out the lane boundary polylines. Finally, we show the output of our model on long stretches of the highway. You can see how well we produce complex lane topologies. In a similar work, instead of lane boundaries, Zarin et al. Propose a model called lane graph net that extracts the directed lane centerline and the connections between the centerlines from multimodal bird's eye view images. Being able to know the exact location of the centerline and the directions enables autonomous vehicles to determine legal trajectories from the current position to goal points. Importantly, we can use other modes of data capture, such as drones, and exploit the aforementioned methods and further save in data collection expenses. Next, Quinn will talk about online mapping.
Hello, everyone. My name is Quinlan Sikora. I'm a research scientist here at Wabi, and today I'll be going over the online mapping section of this tutorial. Online mapping is a must for safety, as maps are not always up to date, localization can fail, and sometimes we might not even have maps at all. Mapping every area can also be expensive, and updating the map when it is changed is also very expensive and difficult to scale. Thus, in such cases, one must be able to generate the maps while driving. However, online mapping comes with its challenges. Occlusion, for one, is a big concern, as mapping elements can often be occluded by objects in the scene, such as vehicles and pedestrians, especially in heavy traffic. Also, compared to offline mapping, online mapping can only detect elements within the range of the onboard sensors. Furthermore, construction elements such as cones and construction vehicles can alter how the map is perceived by the self-driving car. For example, they can block off lanes, and thus detecting them becomes crucial. For self-driving, the software stack must also run efficiently, and thus online mapping must run quickly and accurately, which is always a trade-off that should be properly handled. Finally, we also have to create a consistent map over time, which is challenging due to factors such as occlusion and map changes due to construction sites or other factors. To do online mapping, there are many works that detect the lanes in 2D camera space. They typically use deep learning to segment the lane boundary pixels, followed by clustering the pixels belonging to individual lanes, and then fitting a spline to each individual cluster. Some other works incorporate geometric clues, for example, vanishing points, in order to embed geometric context in the backbone network. However, we would like to stress the important fact that doing precise lane detection in 2D does not imply precise lanes in 3D, which is the space we really care about. For example, in the image below, we show the results of predicting the probability of the lane boundaries in 2D and then reprojecting them onto overhead view. The input camera image overlaid with the predictions from Pan et al. Is shown on the left. The lane probability output of the model in camera view is shown next, followed by the reprojection of the probability output into an overhead view. Although the lane detections in camera view look quite precise visually, the probability output becomes diffuse with increasing distance, and the detected lane boundaries become less accurate in 3D. As seen previously, detecting lanes in 2D can result in inaccurate boundaries due to projective transformation. Furthermore, autonomous vehicles reason in 3D space for other parts of the stack, such as perception, prediction, and motion planning. Thus, it is important to detect the position and topology of the lane boundaries directly in 3D as the autonomous vehicle drives. This is the tasks of 3D lane detection. In this direction, there are works that directly perform online 3D lane detection. For example, 3D LaneNet applies an inverse perspective transform to deep features of a single image to predict the center lines and lane boundaries directly in 3D. Next, the lane boundary predictions are cast as object detection tasks with fixed anchors followed by refinement. They can also handle changes in the topology by predicting two center lines at forks or merges. In contrast, Bai et al. Fuse camera and LiDAR sensors for a more robust 3D lane detection. In particular, they first rasterize the LiDAR inputs into bird's eye view, and then a CNN outputs the dense ground height from LiDAR, which is used to reproject the camera image into bird's eye view. Finally, camera and LiDAR bird's eye view are inputted into a CNN that outputs the lane boundaries. As you can see in this video, this approach produces very precise boundaries in 3D for all of the given lanes. In the context of online mapping, one may wish to make use of the camera imagery taken from different camera views while driving. But how can one process so much information? Fliegen et al.'s paper Lift, Splat, Shoot, camera imagery is used from multiple views and fused to predict a bird's eye view segmentation of the mapping elements. In the first stage of this model, each image is lifted from a local two-dimensional coordinate system to a three-dimensional frame that is shared across all cameras. This is done by predicting a depth for each pixel in the frame. Next is the splat stage. Here, the point pillars architecture is used to convert the large point cloud outputted by the lift step to a 2D bird's eye view segmentation of the scene, which includes the lanes and the drivable area. Here, we showcase examples of this model's output from 6 camera views. Notice how the model is translation equivariant, meaning that if all pixel coordinates within the image are shifted, the output will also shift by the same amount. It is also permutation equivariant, meaning that the output does not depend on the specific ordering of the cameras. And finally, it is ego frame isometry equivariant, which means the same object will be detected in the given image, no matter the camera that captured the image where it was located on the, relative to the ego vehicle. However, mapping as a whole is just a means to an end. So we would like to actually learn representations that are directly useful for the task of driving. MP3 is an end-to-end network that is able to perform interpretable perception, prediction, and planning by predicting an online bird's-eye view segmentation of the map. Mapless driving has much more relaxed requirements and can be just done from sensor data and a high-level command. However, any map-based autonomy stack needs to be redesigned to tackle additional challenges, such as the lack of motion pathfinders. This particular method addresses this by telling us where it's possible to drive while predicting the dynamic occupancy that estimates how the obstacles might move into the future. During the scene representation aspect of the pipeline, they predict the road where the vehicles are allowed to drive, intersections controlled by traffic lights or signs, truncated distance transformed to the lane center lines that we can legally reach, and the nearest direction of the traffic. To define this, we find the closest reachable lane segment for each spatial grid cell and attribute the angles defined by the segment. For dynamic obstacles, we predict the space occupied by the vehicles, pedestrians, and bicyclists for the next 5 seconds, as well as their motion fields. In fact, we frame this dynamic obstacle prediction in a unified parameterization rather than as independent outputs. Next, we compare to the baselines one by one in this simple scenario. We were able to simultaneously predict the drivable lanes as well as the predicted route, as seen on the left, in tandem with the motion and future occupancy of the other actors in the scene, as seen on the right. The network is also able to distinguish between the movement of the vehicles in the intersection and those of pedestrians and bicyclists. We can see how the desired action, which is written out on the left, is automatically able to be integrated into the predicted route as the car goes forward. However, the world is more complex. In Toronto, for example, where I live, we say that there are 2 seasons, winter and construction. These images were captured during the morning commute to work before lockdown. And as you can see, the diversity of appearance and configurations of the construction elements is quite varied. Being able to detect construction elements is very important, as they can change the environment in which the self-driving vehicle is able to operate in. Some works have tackled this problem by purely as a detection problem, whereas in previous works, they're able to segment out elements while keeping track of it using consistent memory. These other methods are able to estimate the construction elements in the maps by utilizing a memory, which is updated every time a new sensor reading arrives. It is multimodal and exploits both LiDAR and cameras, and as you can see, it is able to produce accurate estimates of what elements are in the scene in 3D. We'll now move on to discussing multi-agent routing for HD maps. In order to create HD maps, we first need to send out the fleet of vehicles to collect the raw data. This task can be expensive when covering exceptionally large regions, and therefore can benefit immensely from further optimization. This motivates the need for a system that is able to autonomously map a region and coordinate an increasingly large fleet of vehicles in an efficient, scalable, and adaptable manner. We are therefore presented with the following task. Given an input of an OD and a graph that represents the nodes we wish to traverse, how can we produce an optimized set of routes for the fleet of vehicles? More specifically, how can we autonomously and scalably create and update HD maps of large regions? The idea of an agent or fleet coordination system is not a new one. A similar idea has been explored in the case of the traveling salesman problem. In this problem, we have a series of points on a plane, and ideas for the agent or salesman to visit all of the points exactly once in the most efficient manner possible, and then return to their original starting position. The vehicle routing problem is a natural extension to this with multiple agents. Given a set number of agents, which all start from the same initial starting city, all are expected to visit some subset of points so that after all the agents have finished, every point has been visited exactly once. Bringing this back to mapping, each node could be a representation of the cities that need to be visited, or even individual streets. One class of solutions that fall under the definition of traditional optimization algorithms. These solvers are able to consistently determine the exact optimal solution to relatively large problems, as seen in the case of Concord or LKH3. However, they scale poorly relative to the size of the problem, and therefore tend to be only used in an offline setting. When such solvers are used for large-scale mapping, the initial trajectory is calculated using an iterative solver offline, and the fleet of vehicles is sent out to perform the mapping task, as seen in mapping attempt 1. However, if there are any mapping failures, then the solutions have to be recomputed and the vehicles have to repeat the mapping process, as seen in mapping attempts 2 and 3. This process is repeated until every street has been completely mapped, which, as you can patently see, isn't necessarily the most efficient practice due to the lack of any real-time adaptation. In the deep learning field, a few steps have been made towards more adaptable solutions. Value iteration networks, such as the generalized value iteration network, are able to explore the environment in a learnable manner, but struggle to perform any kind of long-term planning. Graph attention network-based solutions are able to focus on specific sets of nodes within a complex graph, and therefore enable more sophisticated planning and information passing. It should be noted, however, that all deep learning networks do not have the same guarantees as traditional solvers, and furthermore can require expensive large-scale training to be used effectively. The overall graph attention network flow generally operates in the following way. We extract nodes from the map graph, encoding that information, and then send these node encodings to some form of internal node-based graph attention module. This module iteratively exchanges information between each of the nodes and allows for complex planning to occur in a distributed manner. Some form of communication module exchanges node information between each of the agents and allows relevant discoveries made by each agent to be shared. The final output is also returned to the map graph in the form of a per node valued function, which will decide the agent's next action. Here, we showcase how Marvin, an attention-based graph neural network, is able to dynamically coordinate a fleet of vehicles as a swarm in an online setting. Here, we see two attention heat maps produced by Marvin visualized beside each other. The red dot represents the current position of the agent in each scene, and notice how the agent's strategy alternates between focusing on a small set of nearby regions within the subregions and discovering new regions they may want to travel to into the future. The agents will dynamically reroute themselves until the mapping process has been completed. We qualitatively compare the mapping process of Marvin to that of another competitor architecture, specifically that of the generalized value iteration network. We found that Marvin results in more thorough mapping processes, where we prioritize filling in all of the regions completely over exploration. Due to the mapping failures that can occur, and the lack of information where these failures are a priori, ensuring completeness of a region before becomes a non-trivial task in itself. Now, here is a visualization of Marvin at work as a fleet of 20 agents maps a small region of Chicago. We can see how that though the agents begin at the same single starting point in the map, they're able to coordinate online and spread out throughout a variety of different regions in the map. As they expand, they're able to adapt to the mapping failures that occur by sending other agents to remap these regions. Finally, as each of the agents finishes their subregions, they're independently able to return to the original starting position, while nevertheless ensuring that all of the streets are fully mapped. To conclude, we have discussed two types of maps that are employed by self-driving: topological maps and HD maps. I then showcased how to build an algorithm where humans can collaborate with machines to reduce the cost of creating HD maps. Finally, I showed an approach to route a fleet of vehicles to map an entire city in a dynamic and coordinated manner. Thank you very much for your attention.
Hi, everyone.
Cool. So we have actually a question in the Zoom chat for the HD maps session. The question is, what is the process of aligning the SLAM map to the global coordinate system such as GIS? Are there a set of persistent points with known coordinates like manholes that are used for global alignment? And maybe Andre, if you want to take this one.
Yeah, sure, Siva. Can you hear me okay?
Yep.
Awesome. Yeah, that's a great question, and it's a challenging part of mapping. So that can be done. There's many ways in which you can reference these things. In practice, you can definitely use these beacons, but an alternative is essentially just incorporating GPS data, sort of basically, yeah, WGS 84 coordinates, latitude, longitude into the SLAM optimization problem, such that you have sort of this geo-referenced information basically everywhere in your map. And then you can cross-reference this, for example, for navigation purposes. And what you often do actually is A lot of the HD map annotation is actually done more or less from scratch, which means that you don't necessarily need like perfect alignment with, say, OpenStreetMap or something. And in terms of just pure routing, even if you're just routing basically, oh, turn left here, turn right here, then a coarser alignment within like 1 or 2 meters is enough in that case. And then for the annotation, you annotate on your reference frame for exact lanes, and there you have guaranteed alignment because you just built the map. Yeah, I'm checking the YouTube live stream as well, and I don't think there's any questions there either. And the chat should have history, so live chat, top chat, yeah, okay, cool. And nothing on Slido either, so that's good. I think this is everything. Yeah, you're welcome. Hope my answer's clear.
Yeah, if there are no questions, maybe we can take a brief break, and the next session will be the final session. It's for the localization, and we'll start 2 minutes, I guess.
Awesome. Thanks so much, Jinkang.
Cool. We can go ahead and get started with localization.
Hello, everyone. My name is Andre, and I'm a research scientist at Wabi. Together with Shenlong and Julieta, we will be talking about localization for self-driving cars. Self-driving vehicles are one of the most complex and safety-critical modern-day applications of robotics. And leveraging rich maps can enhance performance and safety in areas such as perception, motion forecasting, and motion planning. However, in order to leverage these maps, the vehicle must know its position within them, and this is a task of localization. We begin this talk by specifying what localization is, how it is typically approached, and why it's challenging. Afterwards, we will present a few ways of formulating localization probabilistically, each with their own pros and cons. And after this, we will cover 2 major subtypes of localization, online and global. First, we will look at online localization, keeping track of your pose over time starting from a known estimate. And next, we will show an analysis of how online localization and its errors impact autonomous driving stacks. And we will describe a multitask neural network architecture that jointly solves online localization, perception, and prediction for improved efficiency. And finally, we will discuss global localization, that is, estimating a sensor's pose without any prior information on where it is located. Methods in this family include familiar techniques like place recognition and GPS. Given a sensor observation and a pre-built map, the goal of localization is to infer the location of the car in the map. We focus explicitly on map-based localization, that is, localizing within prior built maps, since this is necessary in order to leverage the HD maps described in previous sections in order to achieve maximum safety. Formally, we wish to model the robot's belief over its state space, where for localization, the state space basically corresponds to its position in the world. We denote the position of the robot or pose at time t as xt, and the observations by z. And we use m to just denote the prior, basically pre-built map. So what kinds of sensors can we actually use to localize? Well, the Global Navigation Satellite System, or GNSS, is a common source of input which is often used in computing initial pose estimates for global localization, which are then further refined with other sensors, such as cameras and LiDAR. Over the last 3 decades, cameras and LiDARs have been leveraged in a wide variety of localization algorithms, many of which will actually be described later in this section. IMUs and wheel encoders are also leveraged as additional cues, as they provide additional information that is complementary to the observations from cameras and LiDARs. In terms of map representations, there's a very wide range of representations that can be used for localization purposes. In the previous sections, we saw how HD maps can be built and annotated with information such as lane boundaries, lane types, signs, etc. And these maps can also be used for localization. 3D geometric models can also be employed. These models can be represented as dense or sparse point clouds, circles, or any other kinds of 3D primitives. Topological maps are possibly non-metric, graph-like representations that are similar to those, for example, found on OpenStreetMap. And they are typically much less detailed than the fully HD semantic maps on the left, but can nevertheless be leveraged for localization. And finally, simple occupancy maps can also be used. They are often represented simply as top-down views of the world. And these maps can also contain additional attributes in addition to this occupancy, like surface reflectance or color. And the added benefit of these maps is that they not only encode rich information about the structure and appearance of the world, but they can also be much easier to store and compress than other representations. So the main characteristics we would like from a self-localization system that's running at scale on a self-driving car fleet are low costs, as we naturally want to map very large areas, the ability to localize in real time, high accuracy, centimeter level localization, and robustness, so the capacity to be robust to errors and to recover from potential failures. However, in order to achieve these goals, there are still some major challenges which have to be overcome. Localization systems must be robust to the presence of dynamic objects in the scene, as they are irrelevant for localization. Geometrically degenerate areas, which are areas that lack distinctive geometric cues, can also be problematic. These areas are challenging for geometric localizers, since observations in this case cannot be uniquely aligned to the map. Sensor noise also affects all sensors in different ways. Multipath effects, for instance, can affect both GPS and LiDAR and can cause difficulties localizing. And finally, environment changes, like construction, mean that localizers must be able to adapt to cases where maps become outdated. So now that we've gained some big picture context on what localization is trying to solve, it's time to dive into some of the mathematical foundations of probabilistic localization systems. We'll talk about state estimation, one of the core subfields of robotics, and see how localization can be cast as a state estimation task. So there are 2 main parameterizations of vehicle pose that are used in self-driving vehicles. The minimal parameterization has just 3 degrees of freedom: the latitude, the longitude, and the yaw of the vehicle with respect to the map. And while very minimal, this representation makes a lot of sense for vehicles, since they travel on the ground manifold, and the other 3 degrees of freedom, namely pitch, roll, and height, can be readily derived from the map. The full 6 degree of freedom representation is more complete and fully describes the pose of the robot in the 3D world. It can lead to more robust state estimation, albeit at higher computational and modeling costs.
It's also required in cases where the on-ground assumption no longer holds. So for example, for drones. Note that we not only care about a point estimate of the location, but more broadly about a confidence measure over the state space. And this probabilistic framework allows the modeling of the uncertainty with respect to the pose, as well as the ability to track multiple pose hypotheses and recovering from failures. In this context, we can look at localization as a probabilistic inference problem. That is, estimating the belief over our state space, which in this case happens to be a position. And mathematically, we can denote our states at time t as xt and our observations, which can be LiDAR, IMU, GPS, you name it, as z. We operate under the Markov assumption, which basically states that the belief over our state at time t-1 encodes all the information from past states, which allows us to predict where we will be at time t. We will see why this is a good idea once we start looking at how this estimation is actually implemented in practice in the next few slides. And by discretizing the temporal dimension, for example at 10 or 30 hertz, we end up with localization as a recursive Bayesian filter, which can be solved with a simple but very effective algorithm. Right now, I'm going to give a very brief overview of how Bayesian filtering works as a framework in the context of localization. But it's very important to point out that this general framework is in no way restricted to the task of localization. It's quite a very broad tool. So there are essentially two main steps in this algorithm that keep getting repeated over and over as the robot moves through an environment: prediction and observation. Each iteration begins with the prediction step. This step uses a propagation model to compute a prior belief over the current step based on the previous state's posterior. So for localization, this propagation model can, for example, be a kinematic model. So since I was at some location 0.1 seconds ago, and my velocity is this value, I will likely be around this other location at the current time, assuming, for example, that my velocity is constant or close to constant. Mathematically, in this equation, the rightmost term is the last step's belief, while the middle one, which is highlighted in magenta, represents the propagation model that is built into our system. So for example, the simple kinematic model I described a few seconds ago. The second step updates the prediction from the past step based on our current observation. And this is basically what integrates new, fresh information from our sensors into our belief. On the right, we see an illustration of a Bayesian filtering procedure. The state space here is unidimensional. It's just a scalar that depicts the robot's position in a corridor. So it's just one number. And the robot at the top begins with basically no idea of where it is. The belief over the state space therefore corresponds to a uniform distribution. And in this case, since we are thinking about the entire state space, this is a form of a simplified global localization, since the robot basically doesn't start with any prior knowledge on where it could be in the environment. Then in the second row, the robot performs its very first observe step and notices that it's near a door. However, this pose is still ambiguous since it cannot tell which of the doors it actually is next to. The robot then moves a little bit and applies its transition model to approximately propagate its old belief based on how it moves. This represents the first step of the second iteration. This increases the uncertainty a little bit, as we can see based on the widening peaks, since direct ego motion readings are typically noisy. And finally, in the second step of the second iteration, the robot finally observes another door and fuses this information with its current belief. This additional information helps us disambiguate the robot's pose, and it allows it to converge to a mostly unimodal distribution over its location. And note that this example is purely conceptual, since in practice, we usually cannot solve the integral from this formula in a closed form. So proper Bayesian filtering results in this integral that is over the state space at the previous time step, and it is often intractable. So in order to solve it, there are a couple of common approximations that we can do to kind of tackle this problem in practice. The first potential simplification is to assume that the distribution is unimodal, transitions are linear, and that both the noise and the belief are Gaussian. This results in the Kalman filter. And Kalman filters, which are widely used, are typically restricted in this case to online localization, which assumes that a good initialization is given to the system. The second option is approximating the integral via Monte Carlo sampling, and this is known as particle filters or importance sampling. Particle filters can be used for both online and global localization. Finally, the third option is discretizing the distribution, which results in a histogram filter. This is easier to work with, but can be computationally expensive. Histogram filters, just like particle filters, can also be used for both online and global localization, though their memory and computational costs can be prohibitive in the global case. So let's look at all of these options in a bit more detail. One of the oldest instantiations of recursive Bayesian filtering is the Kalman filter. And with applications ranging from the Apollo program to modern GPS, it's definitely one of the most common. In their standard form, Kalman filters essentially model linear systems that are subject to Gaussian noise. As such, they are represented as compact and efficient closed-form equations. They are computationally efficient and precise, as well as amenable to a wide range of applications. However, they are limited in their expressiveness and struggle to deal with non-Gaussian noise and highly nonlinear high-dimensional system models. Moreover, due to their fundamental sort of single-mode Gaussian form, they also cannot really model multiple hypotheses and thus struggle to recover from errors. It's also worth mentioning that while Kalman filters can be extended to work with nonlinear system models and more sophisticated noise models, such as EKFs and UKFs, these variants do not share the same theoretical optimality guarantees as the original Kalman filter. The second instantiation, particle filters, bypass some of the limitations of the Kalman filter by using sampling to estimate the probability distributions that are involved in the Bayesian filter and the integral itself. And particle filters are therefore no longer restricted to any particular system model or noise models. This way, basically we can model multimodal distributions as well as pretty much any system and noise model without having to care about linearizing the system or having a linear system to begin with. However, particle filters can still become computationally expensive for high-dimensional state spaces because at the end of the day, you still need to make sure that you have enough particles to cover all of your modes. And as such, you may end up undersampling some of these modes. So careful design is needed to make sure that you have estimates that are stable and do not collapse. Finally, histogram filters are the third option, and they simply discretize all or part of the state space into a set of cells, which essentially means that similar to particle filters, they can support any distribution over the belief space, since you're no longer bound by any sort of parametric solution. So any system and noise model can be employed. At the same time, histogram filters avoid the unimodal collapse risk that particle filters have, and essentially eliminate the need to choose the number of particles in advance, which reduces the number of hyperparameters that need to be tuned. However, by discretizing your entire state space, you have to limit the resolution of your estimate, and at the same time, you essentially end up having to store a very large lookup table, which can be computationally and memory intensive in high dimensions. Later in the talk, we'll actually look at how we can bypass some of the limitations of histogram filters in the context of online localization specifically. So let's look at an example of a toy histogram filter in action. We will see a simulated robot that's attempting to localize using beacons in a 2D environment. The ground truth pose is depicted with a red cross, while the fixed beacon are shown in black. The robot can observe nearby beacons, which is indicated by the black lines. The histogram filter estimates the belief over the robot's pose at each grid location, and the probability is depicted in blue with darker shades basically corresponding to higher probability. And note how the shape of the probability distribution starts off with that ring-like pattern, where the robot only senses a single beacon, so its location around the beacon is very ambiguous. It then converges to this unimodal estimate as soon as the robot sees another beacon, which basically reduces its ambiguity. Note that as the robot moves around, the shape of this distribution is very non-Gaussian, so a Kalman filter would struggle to model this example. However, at the same time, updating each grid cell at each time step is required with histogram filters, which can be computationally expensive. So this highlights kind of some of the benefits as well as the limitations of the histogram filter in practice. Just to recap, we saw that while we can elegantly model a recursive Bayesian estimation using a pure mathematical form, in practice we have to make some trade-offs in order to implement this on a real robot, We saw that, for example, a Kalman filter is able to produce convenient, continuous, and closed-form estimates, but it is limited in its modeling power. Its unimodal nature means that it is unable to track multiple hypotheses easily, for instance. Next, we saw that particle filters can bypass some of these issues and approximate these quantities by sampling. However, the modes of the distribution can still collapse, and the number of particles necessary to model the distribution grows as an exponential function of the number of dimensions in your state space. And finally, we saw that histogram filters can also represent arbitrary system and noise models without risking collapse, albeit at much higher computational costs and with limited resolution. However, later in this talk, we'll see how we can still leverage the best parts of histogram filters together with their robustness without the large computational costs. I'll now pass the torch to Shenlong to talk about how to actually model the observations, as well as to cover the most recent advances in the field of autonomous vehicle localization.
Hello everyone, my name is Shenlong. I'm going to discuss a variety of existing approaches towards localization for self-driving. A common element in all localization efforts is the need to always integrate new observations to reason the states of the vehicle. Observations could take a wide range of different forms, from direct sensor reading to a neural network that perceives the 3D scene. In our previous slides, we saw a few methods for state estimation. Now we will look at a few different observation models. There are a huge number of existing approaches, and for the scope of this tutorial, we will focus on 6 major categories, including real-time kinematic systems, semantic matching, geometric alignment, camera-to-LiDAR alignment, visual place recognition, and LiDAR reflectance matching. Next, I will review them in details. Real-time kinematics approaches use differential GPS to estimate the position of the car. These methods can be very accurate, achieving centimeter-level accuracy, and they do not require prior knowledge about the appearance of the environment. However, the downside include poor reality when no GPS satellites are directly visible, like in areas with large buildings and internals. At the same time, the reliance on the presence of base stations means that the area coverage is quite limited and hard to scale, since extending RTK operations to new areas involving setting up new base stations. Semantic localization, on the other hand, leverages compact maps storing only semantic cues like lanes, signs, turns, and road types, all of which can be stored as vector maps, just like Google Maps we use in our daily lives. At the runtime, the car must recognize these elements and match them against the vector map to localize. Due to the sparsity of these cues, these approaches can hardly achieve centimeter-level accuracy and struggle in areas without semantic cues. Examples of this approach include Lost, which relies on matching visual odometry with OpenStreetMap's road networks, and some recent works exploiting lines and signs for localizing on highways. Geometric alignment methods rely on aligning LiDAR point clouds to pre-built 3D maps. These methods can be very accurate, relying on well-established, conceptually simple methods that can be robust to outliers, such as the iterative closest point cloud algorithms. The downside is that these methods have difficulties in geometrically degenerative cases, such as tunnels or bridges, where you keep seeing the same geometric structures. Further, they usually require a good initialization for convergence. Additionally, storing and building 3D geometric maps can be challenging and expensive. Another line of work is concerned with eliminating the need for LiDAR in localization and only use it for building maps. This has a potential to improve scalability while maintaining the accuracy. While these methods have the potential to reduce the cost of the localization while maintaining centimeter level accuracy, they typically still rely on local search to estimate the vehicle pose. At the same time, the need for mapping dense geometric data still means that a major cost limiting the scalability of this line of work. Place recognition tackles localization through retrieval. In these methods, we try to recognize a place that we have seen before by matching the current observation to a database of pre-localized observations. The advantage of this method is that it doesn't require any initialization and can scale to very, very large areas and used when we need to recover from localization failures. In addition, advances in large-scale retrieval are directly applicable to this problem, making it easy to scale. Unfortunately, however, these methods do not achieve centimeter-level accuracy yet, and they are limited by the density of the used database. More generally, it can be very hard to learn place descriptors that are both compact and discriminative. LiDAR reflectance matching builds a map using LiDAR intensity imagery and matches online observations to this 2D image using simple template matching operations such as cross correlation. These methods can be much more robust than geometric ones, especially in mostly featureless environments. It can be also implemented in a very efficient manner with high accuracy. At the same time, just like geometric alignment methods, reflectance matching methods require good initialization. They also have a relatively high map storage cost. And these methods also require very precise LiDAR intensity calibration, which can limit their scalability due to the difficult nature of this procedure. Recent work has overcome the challenges by learning a deep feature map for matching in an end-to-end fashion. First, we pass the online LiDAR sweep and the map through a separate fully convolutional network to compute the corresponding embeddings. Following the histogram filtering network framework, we then compute a matching score for every pose within a limited search range of our directing pose by fusing the matching results with previous time's pose information and other sensors such as GPS and MU. The search range is over X, Y, and heading, so 3 degrees of freedom. The matching therefore yields a 3D score volume, which corresponding to the observation probability in such a Bayesian filtering framework. A critical component for self-driving is that we need to make it more scalable. So we need to overcome the challenge of storing our HD map to make it cover large operation domains. Ideally, we might consider lossless or lossy image compression algorithms, just like PNG or JPEG or even deep learning image compression algorithms. But remember that these algorithms are optimized for perceptual or reconstruction quality. In our application, however, our map is only used for localization and not for human perception. Therefore, we can learn a compression algorithm optimized for localization tasks. And this motivates us to go one step further. We incorporate a neural compression module within this network to encode the input map to a compact binary code, and we only need to store the binary code on the car. The compression module is highlighted with a gray box, and this compression module is made end-to-end learnable. In other words, learning will decide what information it will keep and what to discard. And unlike prior compression work, it directly optimizes the trade-off between compression and localization accuracy, as opposed to the trade-off between compression and distortion, which is commonly used in general-purpose compression literature. And as a result, we have reduced the storage by 3 orders of magnitude with only a slight accuracy drop. And importantly, our approach is much more storage efficient and accurate than storing maps using standard lossy compression algorithms. Based on our computation, this compression allows storing a centimeter level accuracy localization map for the entire HT US network in a single commodity hard drive. This take-home message is that when designing data compression algorithms for robotics applications, we should exploit the fact that the consumers are our robots instead of the humans, and our goal is to preserve our downstream task performance. Here we show some qualitative results. On the left is our online LiDAR, in the middle is a map, and on the right is our localization results. The vehicle poses predicted by our method is in red and the ground truth is in green. Note that in these cases, we can see our pose and ground truth pose are almost perfectly aligned. I will now hand it over to Julieta to talk about global localization and the importance of taking localization uncertainty into autonomy. Thank you.
Thank you, Shenlong, and hello, everyone. My name is Julieta, and I'm a research scientist at Huawei. I will be talking about understanding the role of localization for autonomous systems and then about global localization. So for all the approaches that we have seen so far, the main objective is to make sure that localization error is as low as possible. However, in self-driving, we care mainly about providing safe and comfortable rides to the user. Notice that these are primarily motion planning metrics. So how can we evaluate motion planning in terms of localization accuracy? Turns out that with the right setup, we can not only link localization to motion planning, but also save computation if we do localization jointly with other parts of the self-driving stack. Let's watch this video together.
Hi, I'm Andrei. I'll be presenting our work on deep multitask learning for joint localization, perception, and motion forecasting. Recently, we have seen a lot of progress on multiple problems related to self-driving, such as perception, motion forecasting, and motion planning. Many of these methods take as input high-definition maps, which can provide a rich prior for these tasks. However, leveraging maps requires precise knowledge of the vehicle pose, which is assumed to be error-free by modern approaches. Like any other system, localization systems can fail unexpectedly. The natural question is then, how robust are state-of-the-art self-driving stacks to localization error? We investigate this problem by simulating localization errors on two state-of-the-art perception prediction and motion planning modules. We benchmark failures on the LP3 dataset. LP3 contains 1,800 sequences recorded in a large North American city. This is a subset of the recently proposed ATG4D dataset, which also includes appearance maps. The appearance maps are necessary to benchmark localization, perception, prediction, and motion planning jointly. For perception and motion forecasting, we simulate a misalignment between the semantic map and the LiDAR reading. The simulated lateral and longitudinal errors range from 0 to 80 centimeters and from 0 to 3 degrees in rotation. In terms of detection, mean average precision is fairly robust to translation error, but suffers a decrease of roughly 7% due to rotation error. In terms of motion forecasting, the mean distance between our predicted trajectories and the actual trajectories at 5 seconds increased by up to 30 centimeters for rotation error. For motion planning, we simulate a misalignment between the map and the output of the P2 module. We run the planner on the first frame and unroll the trajectory over 5 seconds. We observe a similar story. We see a much higher increase in collision rate at 5 seconds due to rotational error. Interestingly, the effect is less pronounced for the distance between the ego car trajectory and the trajectory chosen by the original human driver. We now focus on designing a system that performs localization and perception prediction jointly. We designed the system with 3 goals in mind. First, it should have low latency and ensure its computational cost is small compared to the overall perception system. Second, we would like to leverage learning-based LiDAR localization to achieve robustness to dynamic objects and intensity miscalibration, while also reusing computation from the perception side. Third, we would like our joint system to be easier to train and to deploy than its separate counterparts. The proposed architecture extends a state-of-the-art detection and multimodal motion forecasting network, the implicit latent variable model, with the ability to detect and correct pose errors with minimal computational cost. The pose estimation is done using a deep LiDAR matching approach over 3 degrees of freedom, x, y, and yaw, and the computed offset is then applied to the semantic HD map used in detection, forecasting, and planning. First, the perception system is trained by itself using ground truth object labels and pose information. Next, we freeze the weights of the perception system and train the localizer as a side module, leveraging feature maps from the perception LiDAR backbone. We benchmark our system on the LP3 dataset, focusing on motion planning metrics that measure both safety and similarity to a human driver. First, we show the performance of a system with perfect localization, and how it degrades by introducing localization error just to the planning module or to both the planning module as well as P2. Although our system exhibits some amount of localization error, we see that we are able to match the performance of the ground truth pose system on all the motion planning metrics. Moreover, because we share computation between localization and perception prediction, we can run the localization subsystem in as little as 2 milliseconds. We now showcase some qualitative results highlighting the impact of localization errors on motion planning. The original trajectory followed by the human driver is depicted as a blue box outline, while the planned trajectory is the red box. Other actors are shown as black boxes, and their motion forecast samples from the first frame are the light blue boxes. Note that we run all of this in open loop, so we do not update their predictions, which is why they sometimes might appear behind them. In a normal setting, they would constantly be getting updated. On the left, we see the autonomous vehicle planning its trajectory under localization error, causing it to plan an incorrect and unsafe trajectory that can lead to a potential collision. On the right, we see our proposed multitask system capable of detecting and correcting pose errors, producing correct and safe motion planning behavior. To wrap things up, we show that incorrect localization can have a significant impact on modern autonomous vehicle perception and motion planning. We then proposed a multitask architecture to allow perception systems to detect and correct localization errors, demonstrating its effectiveness on a large-scale dataset. Please refer to our project website for additional information. Thank you for your attention.
So in conclusion, in this work, we quantified the effects of localization error on perception prediction and motion planning and found that a small amount of localization is acceptable for autonomy. Then we designed a joint system that shares computation and features between localization, perception, and prediction, and achieves high localization accuracy at a reduced inference cost. So now let's talk about global localization. The methods that we've seen so far continuously update the vehicle pose over time based on a nearby estimate. But how do we obtain our initial pose, and how do we recover when Bayesian filtering methods fail? This task is known as global localization. The challenges here are, for example, that the same place can look very different due to factors such as weather, time of day, season, dynamic objects, and so on. Another challenge is that obtaining good large-scale training data for this task remains difficult. There are 4 main approaches to this problem. Pose regression takes images as input and directly outputs the pose of the car. This method is extremely fast, but there is a lot of evidence that these methods don't scale very well to, for example, a city. Retrieval-based methods, on the other hand, are slightly slower, and they have potentially larger memory requirements because they have to store the entire observation database, but they tend to be more accurate in large geographical scales. Now, take this with a grain of salt. As neural networks with billions of parameters become more and more common, they are starting to become larger than a lot of databases, and inference could eventually be slower than retrieval. Instead of describing the whole scene with a single vector, we can also extract local features, build a 3D scene offline, and do local matching online for localization. And recently, it has become more common to learn the pooling of local features into global descriptors that can be used to obtain a coarse pose that is later refined with local matches. A downside of using local features is that the storage requirements are worse than those of global matching approaches, sometimes by 2 to 4 orders of magnitude. We have investigated global retrieval approaches in the context of self-driving and designed a large-scale dataset and benchmark for this task.
We introduced PID30M, a dataset for large-scale localization tailored for self-driving applications. For scalable localization in a city setting, we would like a dataset to 1. Be diverse, 2. Cover an entire city, 3. Provide accurate localization ground truth. Our dataset satisfies these 3 criteria and does so at an unprecedented temporal and geographical scale. Our dataset includes images and LiDAR point clouds, each localized with accurate 6 degrees of freedom poses. We also carry a consumer-grade GPS sensor, which we can use to bootstrap localization. Our dataset also provides a set of labels that allow researchers to better understand the limitations of current localization algorithms. For example, we provide sun angle, season, temperature, precipitation, and semantic segmentation as a proxy for occlusion. With over 25,000 kilometers driven, 30 million images and LiDAR readings, and an area of 50 square kilometers collected over 1,300 trips, our dataset is between 10 and 100 times larger than previous datasets released to the community. PID30M provides a challenging benchmark for large-scale localization, particularly suited to autonomous driving. We plan to create an evaluation server for automatic benchmarking and for keeping track of the progress by the community. We hope that our dataset will help researchers develop new and exciting algorithms for this task.
So to recap, in this session, we learned about localization as Bayesian filtering. Then we talked about using maps built offline for localization. And then we discussed an approach to do localization jointly with perception, prediction, and motion planning. So future directions include, for example, improving the robustness through sensor fusion, reducing reliance on priority maps, or doing end-to-end closed-loop learning. All of these are very interesting areas of future work, and they remain pretty much open. And with that, we are finishing the localization session. Thank you so much for coming, and see you later.
Great, cool. That was our last session. We'll have a 5-minute Q&A. If anyone has any questions, feel free to ask. Cool. Well, if there's no other questions, I think we can wrap up the tutorial. Thanks everyone for attending. We really appreciate it. Hope you had some benefits in listening in, and all the materials will be posted later online after CVPR on YouTube, so that people can watch later if they would like to look at anything again. Thanks again. We'll end the session.